bonsoir.
Tu vas bien?
Il nous vient de Grenoble. Tu as joué là-bas à Grenoble, t'as dû faire plein de showcases, plein de
Non,
choses.
j'en ai fait un seul.
Bien, bon souvenir.
Je sais plus, je sais pas te dire.
Là, tu vois tellement de dates, tu sais même plus. Je suis sûr, il y a des fois, tu sais même pas dans quelle ville tu es.
Une fois, je reviens dans des boîtes, le mec dit ça va. Il est fou, mais voici ça va. Mais t'es déjà venu ici,
déjà
j'ai des
venu.
photos de moi, des vidéos. Je dis ah,
Ah bah oui, je suis venu.
zéro souvenir.
Ouais, ça. Après, tout dépend aussi comment tu sors de la boîte là.
Ah non,
on y rentre, ça va, mais.
Nous, c'est 100% en haut. Hein.
Ah oui.
Ouais, que de l'eau. 100% de
Même pas de-
Carré, non.
Ah ouais, je sais pas comment tu fais, pardon. Comment ça va, Pierrot?
Bah ça va super.
P2L se défoule. Et il est là avec nous. Il vient de Grenoble. Il était déjà passé. T'es déjà venu. On s'est vu à Holocène. C'était à Holocène, hein?
Exactement.
Holocène, au grand festival Holocène que je salue, évidemment.
Eh oui.
Qu'est-ce qu'il y a? Désolé, la classe est un peu disciplinée.
En fait, ma tête se défoule.
Ah,
Tu le fous cette histoire là. On va l'écouter comment tu vas
P2L se défoule. Bah, bien sûr.
Il se défoule.
Il se défoule.
Je vais t'entendre comment il se défoule, moi.
Eh oui, tout est sur la cover.
Ouais, ah ouais.
Explication.
Ah ouais? Ouais, ça va. Regardez ça, tu vas
Allez
cliquer, là.
cliquer sur P2L se défoule.
Ouais, c'est carré.
Et bon, on t'écoute maintenant?
Eh bah vas-y.
Oui, c'est l'heure du freestyle. Non pas par téléphone, mais dans le studio de Planète Rap.
C'est trop fort, hein.
Et toujours avec
Je
Projet
me
X Paris.
souviens même de cette émission, j'ai plus ça. C'est quoi, vous avez retiré?
Regarde,
C'est bien. hein.
maintenant c'est dans le studio.
Et là, il n'y a pas de décalage.
Et il n'y a pas de décalage. Bah, voilà, il n'y a pas de téléphone.
Donc pas de décalage, donc pas d'excuses.
Ah, là, il n'y a aucune
Ça
excuse.
aussi.
Non, zéro, jamais.
On t'écoute, mon pote, c'est parti. Et c'est avec PXP Paris. 100 € en bon d'achat à choper pour toi aussi.
Oui. Pierrot des ailes, Planète Rap. Et toi, si on descend comment? J'aime pas voir le temps passer. Jamais je vais porter des montres. Je suis passé devant le bar. J'ai croisé des monstres. Il restait un coup des cellules. Ils sont tout le temps à doser. Je suis tout le temps à poser. Je mets des filons, je suis comme une étoile. À chaque fois que je vois une colombe, je pense à lui. À chaque fois que je pense à lui, je vois une colombe. Je sais plus ce qu'il me disait quand il était là. Sûrement de rester un brave, je les ai vus en panique, fou, menteur. Ils parlaient quand j'étais pas là. Ils ont pas d'ambition, pas de pudeur, ils se confient au barman. Je suis comme un boss, je dois gérer les projets. Je dois gérer la crise de la casse. 21 piges sorti de l'impasse. On n'y est pas totalement, mais je suis pas loin. On s'amusait avec un ballon. C'était beaucoup plus simple avant. On s'amusait avec un ballon. J'ai besoin d'une prise, c'est ma tête qui a gonflé le prix. Elle est sous emprise, c'est pas sa faute mais celle d'un connard qui est rentré dans sa tête. C'est triste, à l'époque je cogitais dans la caisse. Je m'imaginais lui faire sa fête. Y'a les pros et les proches, les gosses, je vais pas tout foirer. J'ai du respect pour la famille, avec le temps elles ont poussé les canines. Tu m'étonnes qu'au Savour on n'était pas libre. On se rappelle tous du silence dans la cuisine. Là j'ai plus l'âge de me taire, plus l'âge de rien dire, je mets des baffes. À la maison c'était la guerre. Tout est plus simple s'il est pas là. Yeah, je me rappelle, j'ai vu trop de trucs. J'ai grandi, ça m'impressionne plus. Je te mets des claques si tu fais la brute. Les souvenirs ils étaient abrupts. Je vais courir, je rentre plus. De toute façon j'ai fermé la porte. J'ai tout oublié dans le stup. Puis j'ai stoppé, j'ai repris la forme. Elle est bloquée dans mes rêves. Elle a changé ma vie, ça a adouci. Les souvenirs amers me bousillent. Trop de fois ça sentait le roussi. Avec elle j'oublie mes soucis. J'ai pas passé le permis, trop peur de me crash. Finir dans un mur à la prochaine route, voir tous ces prochains enterrements. J'ai déjà vécu ça, ça fait pas rêver. J'en ai plus rien à foutre de la fame. Avec des moteurs, des clowns et des camés. Plus rien à foutre de la fame. De toute façon, je suis en guerre qu'avec moi-même, personne peut m'égaler. Y'a pas débat, je suis pas comme eux en face. Y'a pas débat, moi je suis un prince. J'ai des volcans, une grosse sur ma planète. Je suis trop loin d'elle et ça rend dingue. Quoi qu'il arrive, je reprendrai ma place. C'est resté trop longtemps dans ma tête. J'ai déjà dit libérer mon producteur, il est pas fait pour rester en place. Je tourne une page, j'en écris une autre. Je reprends en main tout ce que j'ai laissé. Même si je suis parti, même si je suis loin, je serai toujours à tes côtés. Je serai toujours là pour t'écouter. Je sais qu'en ce moment t'es dégoûté. Et vu ce que la vie nous a montré, un sourire ça commence à coûter. J'aurais pu lâcher mais j'ai pas lâché. C'est classé, nous on se tape. Fini par placer bientôt le festin. Tous mes proches passeront à table. La vie ça va vite, tant pis. Avant-hier j'étais innocent. Demain je serai riche dans le film. Y'a trop de drames dans nos rétines. Putain j'avais la dalle et puis comment on se donne. Je te promets qu'on goûtera la belle vie. Je te promets qu'on goûtera la belle vie. Tu diras que je t'avais averti. C'est fini, c'est mort, je mets la gomme. Je ramène l'orage et le storm. Tes decks sont toujours en forme. Ils ont dit que je passerais pas la suite. Décale-toi sans enfoncer la porte. Tiro des ailes, Planète Rap. Merci pour l'invitation.
Allez, fort, bravo.
Virulent vers la fin, c'est
Bravo.
Bravo.
Rappelle-nous, est-ce qu'on peut te suivre et le projet surtout, Pierrot?
Pyro 2L, Pyro, le chiffre 2, la lettre L, partout, je viens de sortir un clip, extrait du projet, P2L se défoule volume 3, disponible partout. D'où l'explication, se défoule.
Se défoule.
On a capté, j'ai capté.
capté.
On a vu, direct.
Bah, merci en tout cas à toi, merci à toi.
Merci à vous pour
On viendra prendre c'est ce qu'on va faire avec les freestyles de Planète Rap. T'étais déjà venu, tu reviendras peut-être aussi pour qu'on prenne de tes nouvelles au fur et à mesure.
Avec grand plaisir.
Merci à toi.
Merci à toi en tout cas.
Bravo, on s'est régalé. On attend de mettre un morceau peut-être. Mettons un petit peu de dizaine avec Maza.
Ouais, pourquoi pas.
Franchement.
Mais faut mettre fort, faut
Ah, on va mettre fort, on va mettre.
Non, moi, avant la fin du plateau, normalement, cette vidéo.
Imagine les gens dans leur voiture pour se casser sa gueule. Chez eux à la maison, n'importe où. Ils sont en train de-
Ça, faut le
Là,
méga fort.
même si les voisins gueulent, on s'en fout.
C'est pas grave. Il dure 3 minutes, il dure 3 minutes.
Allez, c'est parti dans 3 minutes. Mettez ça fort à la maison dans les voitures. C'est que Black, ça saute ce soir à partir de minuit. Ça s'appelle Focus et la Zazizeli avec Maza.
Moi je suis comme que Black, on va pas trop s'attacher. Malgré le prix, je suis toujours full en fantôme. Et c'est tout se venger, mais non en sachet.
On charbonne comme des japonais, 100 000 € dans un sac à dos. On arrache chaque année, dans un yaka dans ton sac à dos.
Fini le temps d'avant, fini la zizanie.
On vit l'instant présent, fini la zizanie. On parle pas, on n'a pas. On bouge pas, j'paye la note. On parle pas, on n'a pas. On bouge pas, j'paye la note. Les gars sont chauds pas. À mon passage, elle te truc qui fait Ningisa. Un window shopper, elle veut choper la chopper qui fait Ningisa. Des attentes ne faut pas. J'ai mis 2-3 sons dans le top, donc ils sont sur mes coups. Non, y'a pas de contrat. Tu peux devenir ma chérie, mais pas d'intermittence.
J'prends mon temps, dans la loge, j'roule la tête. Les Weston comme mon père, dernier pas est flagrant. Fini le temps d'avant, fini la zizanie.
On vit l'instant présent, fini la zizanie. On parle pas, on n'a pas. On bouge pas, j'paye la note. On parle pas, on n'a pas. On bouge pas, j'paye la note.
attaquer le live. Je crois qu'il y a un nouvel arrivant aussi autour de la table.
Présentez-vous, boss.
C'est la mélo,
Il y a Dela Melo.
ça vient de Kinshasa à la base. J'ai vécu 17 ans là-bas et là ça fait 2 ans que je fais du son.
Eh ben écoute, bienvenue à toi. On y va, on attaque tout de suite. J'ai pas servi fini, bien sûr. Qui est là, comment ça?
À chaque fois,
Attends, non mais on garde le meilleur pour la fin. On garde le meilleur pour la fin. Même si c'est pas totalement la fin, mais.
Ouais, mais vas-y, on va dire ça.
On va dire ça.
Bon, bah, c'est
Ça va bien, Philippe?
Ça va et toi, tranquille?
En pleine forme?
On est là, en pleine forme. Hein.
Tu as tout ce qu'il
Ce
faut.
soir, c'est fort.
Tu as de l'eau,
J'ai de l'eau, j'ai des platines, j'ai de la musique, c'est bon pour moi. Hein.
Parfait.
Tout est carré, un micro, et c'est bon.
Et bon, on y va quand tu veux. Qui commence alors?
On commence avec MD.
Ah bah ça tombe bien, il est là. Ça tombe bien, c'est parti.
Let's go.
On connaît tes gars, c'est des reflets quand je sais que tu sais. T'as zéro preuve de ce que t'avances, donc je vais nier les faits. S'il y a un truc à faire, on le fait. Je suis resté vrai, je suis plus qu'avant. Et ils font peine à moi. Tu penses que tu veux. Je suis dans une GP, sans côté sur mes côtes. Car je te donnerai jamais des jambons et des phrases. J'étais dans ça, pendant que je pense qu'à m'en sortir. Pense qu'à m'en sortir. Elle aimerait que ce soit tout rose comme dans les films. Elle me kiffe son bêtises, tu sais, comme dans les films. J'ai pas tenu mes promesses, tu sais, faut que je fasse du cash. Dans tout classement, faut que je sois au dernier étage. Je vais vers les yeux pour changer de mot, j'ai trop vu ma time. Les autres souvent, je veux pas être de mauvais yeux. Je vais vers les yeux pour changer de mot, j'ai trop vu ma time. Trop vu ma time. Trop vu ma time. Appelle-moi pour qu'on monte, c'est très chaud dans les visites. C'est qu'il me faut pas qu'il m'évite. Attention quand je sais les chiffres ou les problèmes tombent dessus. Faut qu'on reste avec le mec et d'autres façons. Faut que je recompte encore, comme j'ai pas confiance. La ligne est déjà tracée, je regarde à l'avant. Faut que je recompte encore, comme j'ai pas confiance. Je sais que je serai passé, je regarde vers l'avant. Faut que j'empêche des tonnes et des tonnes d'oseille. J'ai un empêche du cœur, tu sais que je t'aime quand j'aime. Je deviens fou quand t'es par dans ces sentiments. On fait d'en bas, je peux pas finir à terre. Elle aimerait que ce soit tout dans tes roses comme dans les films. Les filles sont des bêtises, tu sais comme dans les films. J'ai pas tenu mes promesses, tu sais, faut que je fasse du cash. Donc du classement, faut que je sois au dernier étage. Je vais vers les yeux pour changer de mec, j'ai trouvé ma dame. Laissez-moi sourire, je veux pas être de mauvais yeux. Je vais vers les yeux pour changer de mot, j'ai trouvé ma dame. Appelle-moi pour qu'on monte, il faut d'être très chaud dans les visites. Faut qu'il me faut ma qu'il m'évite. Attention, les problèmes tombent dessus. Faut qu'on reste vrai, on est trop de façon.
On enchaîne avec le petit
de la bête, c'est leur manque de respect qui fait qu'on se la pète. Un chien faudra dire c'est la boîte, tu vas même pas grailler si tu mets sur la tête. Ils ont mangé une big pizza pour finir au soleil, pas loin du pizza. C'est qui ça, j'arrête, c'est qui ça, y'a ma cour en encre sur les cuissons. 2015, je devais Scott, je crois que la vague t'es comme une escorte. Y'a trop de caméras, y'a trop de buzz. Même quand on finit, lève pas les scores. Je vais faire la caïra du coup. Même si je pense à voir, il a dit quoi, screen, il a chaud, il s'aide. On s'est mis skin, on les scam, et on regarde les scams. C'est une question de mentalité. C'est une question de mentalité. Avant tout, mais t'es pas valide. La ligne, coup, mais t'es pas valide. Fais la base des sympas. Fais la des sympas. Fais la base des sympas. Fais la des sympas. C'est une question de mentalité. C'est une question de mentalité. Avant tout, mais t'es pas valide. Allez, le coup, mais t'as valide. Fais la base des sympas. Fais la des sympas. On a stylé ça pas valide. J'en ai fait une banalité. Les bras c'est faux plus que le cadavre. Tu dois baisser le ton et j'ai pas d'arme. La mouche dans les gradins. T'appelles ma soeur. Je me sens comme une tête devant les hommes. Ma personne a fait sonner les pommes. C'est le sens même coloris que la tortue. On a sorti l'automatique. Depuis le buzz ils sont problématiques. On s'en parle à tout le monde comme mais tu connais ma type. Les mots ça nous fait c'est problématique. Veulent pas écouter mais on leur a dit. Veulent pas écouter mais on leur a dit. C'est qu'une question de mentalité. C'est une question de mentalité. On beaucoup mais t'es pas valide. Allez écoute mais t'as pas dit. Et là-bas c'est sympa. Et là c'est sympa. C'est qu'une question de mentalité. Je reprends du poil de la fête. Je reprends du poil de la fête. De la quoi? Je reprends du poil de la... Ok. Focus. Toujours. On enchaîne avec ça.
Choquer l'écran s'installer, vraiment au poignet, j'ai les choses carrées. Pas le temps quand j'attends, ils nous croient dans des vies paillettes. On a touché la précarité, mais c'est tout dans la tête, on a su se relever. Donc j'ai fini par guitariser. J'étais dans la cour, donc j'ai guitarisé. Oh, je voulais pas que la street me fasse revenir à zéro. Et comme je voyais loin, bah j'écoutais en géo. Je rêve, je peux pas te forcer à même. Nous deux c'est pas la même. J'ai pas les mots, je nous vois pas dans le long terme. Pour ça j'ai pas les mots, 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 pour ça j'ai pas les mots. Et mon passe-temps crée un impact. J'ai ma seule place, je suis pas dans le pack. Pour mes poches, je pouvais traîner dans le bac. J'ai la main d'or, j'écris des pages sur page. Regardez, je pouvais faire pas sur passe. Et je pense que je faisais de la caille en classe. Trop de proches qui enchaînent crasse sur crasse. Pas de bac et pourtant je passe sur crasse. Pas de bras, je voulais pas, je me connais pas. On me disait tu peux le faire, de temps en temps j'y croyais pas. Sans engin, après les coachs, tu m'arrives pas. J'écris dans ma chambre et pour mes gosses, il faut un héritage. Tellement, je suis bon aimant. La télé pour que les gens voient mes flots et mes mots. Tellement, je suis l'élément. Je peux pas te forcer à même. Nous deux c'est pas la même. Pour ça j'ai pas les mots. Tu nous vois pas dans le long terme. Pour ça j'ai pas les mots. 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 Pour ça j'ai pas les mots.
Dans la chambre, pas de tous, elle est castée. C'est une prime, regarde dans les highs. On le l'aime, regarde dans les Donc je bosse comme un boss, pour devenir un boss. Je mets mes problèmes sur le côté et je bosse comme un boss. Bosse comme un boss, je mets mes problèmes sur le côté et je bosse comme un boss. Ouais, j'ai tout raconté ma vie. J'ai verré le bonhomme à vie. J'ai verré le bonhomme à vie. J'ai tout de mon couteau. J'ai obligé d'en poser un pièce. Donc je bosse comme un boss.
Magnifique, qu'est-ce qu'on pense?
Ah si, je sais. Non, c'est
You work when you're on the road. You carry studio around with you. You get up in the middle of the night. You get an idea for a tune, and you get up and go do it. From Detroit.
Baba à l'instant sur Skyrock, c'est le Planète Rap entre 20h et 21h sur Skyrock et on va retrouver Que Black. Est-ce qu'on sait où est passé Que Black? Parce qu'il est sorti avec tout le monde d'un seul coup. J'ai dit au revoir mais tout le monde est parti. Sauf que Black, normalement, oui, je veux bien qu'il y ait. Merci Hello. Tu peux me retrouver Que Black? Ah bah voilà, il est derrière la vitre, on va le retrouver. Non mais attends, qu'est-ce que c'est que cette classe? Je suis tout seul. Le Planète Rap entre 20h et 21h sur Skyrock. Et on va retrouver donc Que Black ce soir sorti à minuit. Non mais attends, Que Black. Tu laisses le prof comme ça tout seul en galère. Tu laisses le prof en galère comme ça tout seul.
Mais la sonnerie là, c'est sonnerie.
Mais il n'y a pas de sonnerie. Tu pensais avoir entendu la sonnerie, j'ai vu que tout le monde était parti.
Regarde,
mais
la cage elle est vide.
Mais la sonnerie n'avait pas sonné.
Ah ouais.
Donc toi tu es retenu pour l'instant.
Ouais, mais...
et tu es retenu pour des questions qu'on va voir tout de suite sur le tableau.
On y va.
Des questions d'auditeurs et auditrices de Skyrock, c'est parti.
Okay.
Planète Rap. Planète Rap. Pose ta question.
Et le premier à te poser une question, c'est Ojiman de
Salut Que Black, est-ce que t'as des nouvelles du projet Congo avec Gradure?
Ah, le projet Congo avec Gradure.
Bah écoute, moi il y a beaucoup de morceaux que j'ai écoutés, j'en fais partie. Mais vu que c'est pas moi qui est à la tête de ce projet, donc j'ai pas forcément de date.
Mais en date,
ça continue.
Ah, ça continue. Pour l'instant, 2025.
Je vais même pas m'avancer.
Ah ouais. Si tu me dis que ça commence à enregistrer.
Non, ça a déjà
ça continue partout.
Ouais.
Je mise pour 2023, mais bon,
on verra bien.
on n'est pas à l'abri d'une surprise. On n'est jamais à l'abri d'une bonne surprise. Autre question pour toi, c'est Anas de Paris.
Salut Que Black, t'en penses quoi de la situation de Mbappé?
Ah, toi qui es très fouteux.
Moi je me pas fou du tout, moi.
Toi qui es très fouteux, qui analyse le football français.
Non, mais j'ai entendu que ça se passait pas très bien.
Le Real, c'est dur.
Le Real, c'est un peu compliqué, mais je sais que...
C'est que Kylian, moi j'en ai marre des gens qui... Moi, tu sais quoi,
c'est les mêmes gens qui vont être là le critiquer.
Voilà,
quand il va revenir en pleine forme. Ah, mais c'est le meilleur.
Moi j'en ai marre. J'en ai marre de ça.
Pour moi, il arrache tout. Il a jamais arrêté d'arracher. Il va continuer.
Je suis d'accord avec toi. J'en ai marre. On peut pas d'un seul coup aimer, puis hop, dès le lendemain.
On a vu ça avec plein de gens.
Alors oui, peut-être qu'au Real, il faut toujours un temps d'acclimatation.
Bien sûr.
Voilà, c'est normal, attends.
Bien sûr.
Et t'es là, en France, bim, il se retrouve d'un seul coup dans un...
Là-bas, il faut qu'il a pas réussi à jouer avec tous ces gens.
Bien sûr.
Exactement.
Moi, je j'ai toujours cru. Non, mais c'est vrai, c'est un exemple incroyable.
De persévérance et tout.
Il est là, et non, mais surtout, c'est ce qu'il y a de beau. Il faut croire en ses rêves. Tu te souviens des photos, il est tout petit, on le voit avec les photos de Cristiano, où il est là, où il rêve d'aller au Real.
Est-ce qu'il savait qu'aujourd'hui, ça allait être un des meilleurs joueurs?
Je pense pas, mais en tout cas, il avait ce rêve. Il s'est donné les moyens pour réaliser ce rêve. Et on peut respecter ça. Et moi, je pense qu'en effet, cette situation-là continue à parler, mais cette situation, quand il s'est un peu dégagé, parce qu'on a des soucis, on est
vrai. Là, il va revenir à fond.
On a tous des. T'as déjà été comme ça, je suppose.
Bien sûr, vous accorde des choses comme ça, mais non.
Même perso en tête, et tout, ça se passe pas bien. Et pourtant, tu souris parce qu'il faut aller en concert, parce qu'il faut aller en chantier.
Voilà,
Que Black, c'est fini. Là, maintenant, la sonnerie. La sonnerie, ça y est. La retenue est faite. Mais tu vas revenir demain. Ce soir, minuit, tu fais quoi? Tu dormiras ou tu vas quand même attendre les premiers retours?
Je pense là, j'essaie d'accumuler le sommeil bien, parce que je sais qu'on n'est pas à l'abri d'une fête. Une superbe fête. On va boire que de l'eau.
Bien sûr. Bien sûr.
Oh oui.
C'est important. Il faut s'hydrater. L'hydratation, ça.
Ouais, franchement, on a pour bien.
Il faut toujours s'hydrater.
Le bon fonctionnement du corps, il faut
toujours. Et avec une belle pureté, je vois déjà.
Ouais, mais c'est des façons. Le DJ, lui, particulièrement, il est dans ce truc-là.
C'est de l'eau suédoise.
Ouais.
C'est pas de l'eau suédoise.
C'est dans une bouteille de.
Ça fait des volcans sur le Bon, merci en tout cas. Merci à toi, Que Black. Rendez-vous demain pour la suite.
Demain.
Ne loupez pas la sortie. Évidemment, demain dans les magasins et ce soir à minuit, juste après la radio de Diffoul. Bim, vous cliquez sur l'album de Que Black. Merci à toi. Rendez-vous demain.
Ok.
Et là, c'est en effet Diffoul et toute l'équipe de la radio libre sur Skyrock.
Et oui, Fred, merci Que Black. Et rendez-vous donc tout à l'heure à minuit. Et puis là, tout de suite, c'est sur Planète Rap à partir de 20h. Nous, on est là jusqu'à minuit, justement. Profitez-en. Appelez-nous au 01.
early engineers wanted to drop an image on the 404 page of the early website and went onto a stock image website and as a reference to an octopus merge, grabbed an Octocat randomly.
Okay, so we have Mona, she's the OG, but like there are a bunch of other variants of Octocat as well. So why are there so many?
We found that the community responds best to all the individual ways that you make Octocats specific. So they can put the stickers on their laptops or wear shirts or make it their avatar on GitHub. And we can only do that if we had a bunch of different versions of it.
Okay, so talk to me a little bit about the design process. Like how do you come up with an idea for a whole
We think of her as a mascot for the open source community. We want people to like her. We don't want to turn her into some corporate shill. We just make sure that she's never selling anything. She's not looking at the camera teaching anything wrong.
It's a true rumor that you're working on a new design.
Yeah. You can look at it right there. The idea for this one is we wanted an illustration we haven't done before. Mona with the new brand Copilot. I always like to work in Easter eggs that are very developable. You notice like the shape of the wings. There's a commit symbol on the side of her helmet with a bunch of iconography and references to the Git graph. Only the super fans are going to get it. But that's the kind of care and intention that we put into these things.
How do I go from this design into the sticker?
Oh, that you're going to have to talk to Lavinia for.
To Lavinia we go. Hey Lavinia.
Hey!
So what do we have going on?
We are here printing GitHub's newest sticker.
I know that GitHub is a sticker company, but do we do anything else?
Actually, we're not a sticker company. Even though we did sell over 100,000 sticker packs last year, that is close to 1 million stickers.
What else do we sell in the shop other than stickers?
I mean, we sell hoodies, hats, joggers, really anything that a developer would want to wear. You really should have Hyper GitHub. I think the ultimate developer. And finally, we have the Art of Octocat book, which outlines the whole history of Mona and how Mona basically became one of our coveted stickers.
Okay, definitely gonna have to check that out. Now, when it comes to the stickers, what different designs that you're featuring?
Octocat, my identity is I live on rock music. I use that on my laptop to go really get a
Now, what happens next?
So we get the art asset from Cameron, and now we send it to our trusted sticker printer, and it goes through a big sampling process in terms of us making sure that the quality is up to par.
Oh, hey, I didn't see you there. Look at this. This is one of the very first stickers off the line. So we had gone from ideation to final form. I need to find a laptop to put this on. I want to thank Lavinia and Cameron for walking me through all this stuff, and I'll see you on the next Inside.
The birthday paradox says if you have 23 people in a row, there's a 50% chance that 2 of those individuals out of the 23 share the same birthday. If you don't think into that too far, it doesn't make sense, right? Like, wait, 23 people, there's 365 days in a normal year. That's how you get to that point where it's a 50% chance. So the joke is you go to a pub that's got like 30 people in it, 40 people in it, and you say, hey, random person sitting at the bar, I'll bet you a beer that 2 people out of this bar full of 40 people share the same birthday. And you're hoping they say, 40 people, there's 365 days in a year. Oh, you're an idiot, I'll take that bet. Because otherwise, we have something called duplicate initialization vectors. And there's a cryptography attack called known plaintext attacks. In fact, if you go way back to the world of web, wired equivalent privacy, that was one of the issues is somebody would use a tool like Aircrack NG, they would disassociate you from the network, and you join back on again. That's okay because I know what it looks like in a plain text form. And I use the MAC address to populate the values, and now I've got a known plain text that corresponds with the resulting ciphertext. You can see monkey has the same hash each time, but if we change that to monkeys, it's got a completely different hash. We use hashes for things like password security or password storage.
Everyone is Ted Koppel back with amazing Steven Greta back in
Great feedback. I like that we're doing this more often now.
Yeah, I really appreciate you taking the time and sharing your knowledge and expertise with all of us. Just for everyone who doesn't know Steven's been a hacker for many, many years. He's also one of the authors of this book, fantastic book. But Steven, really important to highlight. You created a YouTube channel. It's been a while now, actually. So perhaps you can tell us about this YouTube channel and why you created it. Just for everyone who's watching, please go subscribe to Stephen's channel. I think it's a fantastic channel. I get a lot of pushback sometimes by David, you're just doing basic stuff. But Stephen, you've done advanced stuff, but you're also doing a whole range of other stuff on your channel. So perhaps you can just tell the audience about your channel.
Yeah, for sure. Thanks. I started it off about 2 years ago now. Actually, David, you were one of the first people to reach out after the channel. I think it was only live for a month or two. And that really helped me out, of course, to get some visibility. So I always appreciate that. A lot of times on YouTube or other broadcasting networks or platforms, whatever you want to call them, that there wasn't as much or isn't as much advanced content as I had hoped to see out there. And having been teaching for a long time, I get, of course, a lot of people saying, hey, I can't afford to go to a training class, or I'm looking for certain content that I just can't find out there, whether it be browser exploitation or kernel exploitation or fuzzing and all kinds of other topics in the vulnerability research space. So that was kind of the initial goal, was to get back to the community and provide, either from myself or from a lot of guests that I have on, their expertise to share that with the public.
But you don't just do advanced stuff, you do a whole range of stuff now, right?
Yeah, I started off really wanting to focus on nothing but vulnerability research, but it actually expanded out. I've had people on, experts come on to talk about blockchain and smart contract security, ICS security, the website of things. So we just had one the other week on multi-factor authentication bypass. We're doing interrupt pivoting. So mostly on the offensive side, but I also like to have some people on occasionally from the forensic side, especially so attackers, we also think that we're very quiet, we're like ninjas moving through the networks. But in actuality, it's usually due to the fact that they're not really watching the logs very well, and we're not in fact very quiet. So it's helpful to get a deeper forensic perspective so that we can lower our footprint.
I'm glad you mentioned crypto, right? That's what we're talking about today, but it's not the crypto that other people might mistake this for, correct?
Yeah, and this came out of the last session we did on the dark web, and we were looking around at some things, and I think I was demonstrating some stuff using GPA, the GNU Privacy Advisor, and PGP or GPG, and how your OPSEC needs to be really strong, and how some people lack fundamental or foundational knowledge about cryptography, which is so important if you want to obviously do anything from protect your data to securely converse with someone or many other things.
I mean, I think it's really important to have, you've got to know the basics of it before you can. Some people just like want to run before they can run. And I mean, cryptography is such a basic part of what the world represents. The whole world runs on this stuff. I'm hoping I'm not jumping in. I'm hoping that's the kind of stuff that's really fun.
Yeah, absolutely. Like you said, understand the basics. It's really important to know the very basics and how it all ties together. I mean, something as simple as a key exchange or a digital signature can be quite confusing to folks. So it's a good one to know.
I'm going to keep quiet now and give it to you, Stephen. A lot of the audience complain if I interrupt you, so please take it away and I'll ask some questions along the way. But looking forward to it.
Alright, so I didn't know what title to give to this presentation, so I'm just calling it Introduction to Cryptography, but of course we'll talk about the security ramifications and considerations as we go through things. So the items that we're going to be covering are we'll look at some basic cryptography. Obviously this is not going to cover all of the things. There's so much cryptography that we just don't have the time to get into, but I want to talk about some of the basic forms of encryption that oftentimes are mixed together into an algorithm to provide the confidentiality that we want. So we'll talk about some basic items like XOR and substitution ciphers or addiction ciphers. So then again, these things are all mixed in together to create some efficient algorithm. After we get through the basics, we're going to talk about the two primary types of cryptography, meaning symmetric key or single key cryptography, and then we'll jump into asymmetric key cryptography, which is a two-key system. Underneath symmetric key cryptography, there's two primary categories. One is block ciphers, and the other one is stream ciphers. So I'm going to draw on the screen as best I can. I'll warn you that my drawings are not a very good artist when it comes to that, so I'll do my best, and it really does help explain things when you're drawing one component at a time while you walk through. So that's why I chose to do some of the explanations via presentation. You'll see I have some diagrams together, and other ones I'll be drawing on the screen to be able to talk through things more clearly. Then again, we'll get to asymmetric key cryptography, also called public key crypto systems, which we typically use to generate or concept of trust. I'll talk briefly about that as well. That is when you have someone else vouching for you. So just because I say that I'm some actor, I'm Brad Pitt, and I'm communicating to you, and if I can trick you into thinking that that's true, and we use cryptography and I sign it, you might believe that it actually is in fact from me. But if we don't have anyone vouching for us saying, hey, I know that in fact that really is Brad Pitt that you're talking to, then obviously we lose a little bit of security there, credibility there. In order to understand digital signatures, we have to understand hashing. So we'll look briefly at some hashing examples and how that factors in. I've created some pretty, I hope, decent diagrams to help explain this. And then at the very end, I want to mention something called steganography briefly, which is how we hide and embed or inject or substitute data inside a host file. So not only are we getting that confidentiality because I've encrypted something and I'm not sharing the key or the passphrase, I'm also maybe hiding that encrypted data into a host file so that you don't even know that something's there. My quick analogy, and I may say this again later on with steganography, is like if you came into my house and you saw that I had a giant safe sitting in the corner of the room and it was locked, you don't know what's inside of it, but you know that I'm hiding something. With Stego, my analogy would be that I actually hide that in the wall and I put a portrait or a painting over top of the safe so you don't even know that it's there. That's kind of what we get into with steganography, and I'll tell you some examples of how Stego is used and who the biggest users of Stego are. So first off, basic encryption examples. Again, this is not complete. There are so many different variations of things. I'm not a mathematician. I know that the funny joke is that math is a 4-letter word, and I know some people say maths, some people say math, so either 4 or 5 letter. Some people stay away from that their entire life, just like some people stay away from learning how to program their entire life. And as someone that works in the offensive space, I think in this day and age it's really important, as a defender as well, that you have some level of programming or scripting experience. And I say the same thing about cryptography, because if you're a pen tester or a red teamer or someone just assessing a cryptographic implementation, as long as you have some foundational knowledge, there's nothing that should be preventing you from being able to assess that implementation. And as someone who is reviewing or assessing an implementation, a cryptographic one, we typically don't have to get into the world of mathematics. There are, of course, cryptanalysts out there and others who are taking a look at the algorithms or the ciphers that have been created and the mathematics behind it and try to look for some type of vulnerability or weakness in it. But again, when we as a community consider a cryptographic algorithm secure, that's typically done by way of years of public intense scrutiny. So it's not like some company says, hey, we created a great new algorithm, you should go use it. It's typically everything about it is transparent and it's public and anyone can review it and assess it. And when you have years of brilliant mathematicians and cryptanalysts studying it, trying to break it, and they don't find something, then that's when we tend to deem something to be potentially secure. And then at some point, as computing power ramps up even more and more, something called the key space that I'll talk about as we get into some of these examples as well, needs to be taken into account, because the greater the key space, the harder it is, or harder it should be for someone to do like a brute force style attack to try to guess every possible key in the key space, which would then of course let them decrypt your data. So we'll get back into that type of stuff as well coming up. So let's start off with a very basic example, which is XOR, or an exclusive OR. This is a Boolean logic operation. You might have heard things as well like AND and OR. And from a reverse engineering perspective, you might see an instruction that says test, and then it says a register, like the contents of a register, against the number 4. And what that's actually doing, that test instruction, is a bitwise AND operation. So a lot of times we'll have data shown as in something like a bit mask. Think of something like a TCP flag. So in communications over TCP IP, in the TCP header, we have these flags like SYN and ACK and PUSH and FIN. That's working as a bit mask where the ordinal bit position within that array, each of those are flags. They're indicative of something. And if it's a 0, it's off. If it's a 1, it's on. So we can see if the SYN flag is on or off. And if we do something like a test, we're actually checking to see if a certain bit within that bit mask is on or off. And then we make a decision based on that result. So this is another example of a Boolean operation. When it comes to cryptography, we use XOR or XOR, however you want to pronounce it, to take two inputs, which are going to be ones and zeros, but we only take two inputs, and then from those inputs, we produce a result. And that result's either going to be a 0 or a 1. You may have heard of things like truth tables as well. So the word cat, C-A-T, in all capital letters, that is ASCII. When we represent that data, we use something called an ASCII hex table, or the hexadecimal representation. And I'm going to jump over to a Linux system here real quick just to show you how you find this. So let's take a look at the ASCII table by typing man or manual ASCII. And what that brings up here is the ASCII table. And you can see, look over to the far right, I'm going to highlight that at character, the at sign. Next to it, you see 40. So 40 is the hexadecimal representation of an at sign. And then in decimal, that's 64. So when you saw cat on the screen, you saw C and then 43 next to it. 0x, which means hexadecimal or base 16, and then 43. An A is 41. And then if you go down to a T, that's hex 54. So that's where we're getting this from. C is 43, A is 41, and T is 54. Now in binary, if you were to take a calculator, and this is in scientific mode or programmer mode, if we go and take a look at base 16, and I know it's probably tiny, but if you bring up the Mac or the Windows calculator and you choose base 16, and then we can enter in hexadecimal 43. So automatically when we enter 43, again, it's really small, but below that in binary, it shows you that value. And it says 1000011. And if you look on the screen over here to the bottom left, 1000011. And that's the letter C. So these are the different numbering systems. We've got base 2, which is binary, base 10, which is decimal, and base 16, which is hexadecimal. And in computing, we need to learn how to read all of those. You might hear somebody say everything's ones and zeros in the computer, but in fact, like opcodes and things like that on Intel or another processor architecture like MIPS or ARM, those opcodes are typically represented in hexadecimal, as well as the operands and the operand values. But at its core, you can certainly convert base 16 over to base 2, which is binary, and you can look at this data and how to represent it in different numbering systems as you see fit. But back to the point, if we want to take the letters C-A-T, capitalized, which is cat, and we want to see its representation in the ASCII chart, hexadecimal, you can see it's 43 for C, 41 for A, 54 for T. And then if we represent that in binary on the bottom, you can see we have CAT and the binary representation directly above those letters. And this is important when we're doing something like XOR, because remember, XOR takes in 2 binary input and it produces a 1-bit binary output. So if we drop down, here's an example of encrypting with XOR. And some people, you might have heard it before, people say perfect encryption. When somebody says perfect encryption, in my experience, what they typically mean is someone has like a run book or some kind of a book where you have a copy and someone else has a copy, and there's only 2 copies of this book in existence, you hope. And on each page is going to be a key, and that key, let's say it's represented in binary. So in our example here, we want to take the word cat, as you can see up top in green, and then we want to XOR it against the key. In this case, it's dog. When we are doing something like using stream ciphers and generating a key stream and using XOR in these operations, we typically want the key to be equal to the length of the data that we want to encrypt. So in this case, we want to encrypt cat. So we're going to get an equal length value to XOR against that, which we're choosing dog. So you can see in blue is the binary representation from the ASCII character set of dog, and it's equal to the length of cat. So if we want to encrypt this, we would then take the 2 inputs, one at a time, and we produce the output. So with XOR, if the values are the same, if it's a 0 and a 0 being XORed together, or a 1 and a 1 being XORed together, that produces a 0. So over on the right, if we XOR 1 from the first 16, and as you go left, you keep doubling that value, its representation. So if we start at the right, that's the ones position, and it's on. So we take that one. We move over one bit, that's the twos position, and it's on. So now we got 2 plus 1, that's 3. Then we move over one more bit to the left, and it's on, and that's the fourth position. So we have 4 plus 2 plus 1, and that's where we're getting that 7 from. We do the same thing over here in the middle, and the same thing over there on the right. I'm not sure why Ciphertext decided to let the 2 go off to the right there, but 5 is supposed to be one word. So I'm calling this our ciphertext because let's go back to that example where I said this would be perfect encryption if we never use the key again. Pretend that you received the data in the red. You intercepted it somehow, and the messenger had it in their hands, and you seized it, and now you have that binary or that hexadecimal representation of the binary, and you want to decrypt it. But you don't know what the key is. You don't know that the key was dog. You could try every possible value and XOR, try every possible key within the key space and XOR that encrypted data against it. You would then recover plain text, but how do you know if you got it correctly? You might get back the word car or fat or car or many other 3-letter words. You would never know that cat is the right one unless you knew something about the message or you were able to compromise the key that was used. So if we go back to the example of that run book, and we've got pages in it, and we've got one duplicate set. So I've got a copy and David has a copy. And I say, David, I'm sending you a message. Or maybe I don't even tell him, and he receives a message. And he knows that no one has used the current key that's on the first page of our run book, which is dog in this case. So he knows to use dog to XOR against that encrypted data. And the same way that we XOR to encrypt the data, we reverse it to actually recover the data. So again, since David receives the encrypted data, which we put up here in the red, and he knows that the dog key has never been used, he writes that out in binary and then does that same XOR operation. So the 0 and the 1 produces a 1. 0 and the 0 produces a 0. So remember, the numbers are the same, it produces a 0. The numbers are different, it produces a 1. He's able to XOR the encrypted data or the ciphertext against the key of dog, and he recovers cat. And now what we would do is we would burn that page in the run book, and we'd never use it again. And on the second page would be the next key that we're supposed to use. And let's say David encrypts something and sends it to me. I receive that data. I know now to use the key that's there in the run book. I burn that page, and that's why some people call it encryption, because it's one time. You're only using these keys one time, and you're never reusing them. Hopefully I didn't overcomplicate that at all, and you understand like basic XOR operations and how we can use that for cryptography. Now most of us would never rely on XOR alone as a way to encrypt nodes, but it is an important part of many crypto systems. space, which is why we need to make sure that our key space is large enough. If you go back to like an example like DES, Data Encryption Standard, it came out in 1975, a long time ago. I believe the first example of DES was only 56-bit encryption. And then you may have heard of triple DES, which gets us up to 168-bit encryption. So it's much stronger to use multiple keys. That key space, increasing the size of the key space is really what we're counting on to make it so it's going to be hard or difficult for someone to try to brute force all the possible keys in the key space. And I'll explain that more when I show you an example of how stream ciphers work. But again, to take a step back, I encrypt data with a key. David has a copy of this key. He can then decrypt the data with that same key. So it's really important that we protect that key. So I'm going to do some drawing now, and I apologize that my drawing skills are not great, but I think it should be helpful. I'm going to explain the difference between stream ciphers and block ciphers. These both fall into the category of symmetric or one-key crypto system for cryptography. So we'll start with stream ciphers. Let me jump over to my drawing pad here. 6 bits, right? Now remember we talked about XOR before, a little bit earlier. I was saying that XOR and the numbers are the same. The numbers are the same, like it's a 0 and a 0 and a 1 and a 1. That's going to result in a 0. If the numbers are different, then it produces a 1. So we're going to XOR the key string against the plain text. So let's pretend that the plain text is 111010, and that represents, remember the ASCII chart I showed you how we did that mapping with the calculator? Let's pretend that looks like. I know what it looks like encrypted because you sent it out and I sniffed it. I XOR those together. I recover the key stream that's associated with that initialization vector, which is a clear text attribute. So if I ever see a duplicate initialization vector, I'm able to then recover plain text that I shouldn't be able to recover because the encryption key was the same. Even though I don't know the key, I know the key stream of that key with that associated initialization vector. So the question then becomes, what's the best way to handle the initialization vector? Do we want to randomly select it out of the 2 to the 24 power key space, or do we want to sequentially select it? Now the answer always sounds like random, right? Random is usually the right answer, but in this case it's not the right answer because it's something called the birthday paradox. The birthday paradox says if you have 23 people in a row, there is a 50% chance that 2 of those individuals out of the 23 share the same birthday. If you don't think into that too far, it doesn't make sense, right? Like, wait, 23 people, there's 365 days in a normal year, and you're saying 2 people out of 23, there's a 50% chance they share the same birthday? That doesn't make any sense. It's because we're not thinking about it properly. If you were to put all 23 people in a circle, and you drew a line between every single pair so that everyone has a line connected to everyone else, fully meshes, that's how you get to that point where it's a 50% chance. So the joke is you go to a pub that's got like 30 people in it, 40 people in it, and you say, hey, random person sitting at the bar, I'll bet you a beer that 2 people out of this bar pool of 40 people share the same birthday. And you're hoping they say, 40 people, there's 365 days in a year. Oh, you're an idiot, I'll take that bet. When in fact, once you get from 23 people to 40 people, you're up at like 80-90% chance that there's going to be a match, that there's going to be a pair. Similar to like roulette. When we play the game roulette, you go to the casino, and you see the numbers 1 through 36, and maybe there's a 0 or double 0. When the croupier spins the ball and drops in 16, they usually put like a signboard or a placard up next to the roulette wheel. And it's to like trick people, it's to take advantage of people, because people will see, whoa, 16 hit twice in a row. What are the chances of that? Well, it's the same chance of 15 hitting after 16, right? Why would it be any different? Sure, there are variables, there are factors such as the wheel speed and velocity of the ball and all that stuff, but without factoring those things in, it's just as likely for 16 to hit a second time in a row than it is to 15 or 0 or something else. And we don't actually remove that number from the wheel once it hits. And that gets us into the birthday paradox problem here with our key space of 2 to the 24th power with initialization vectors. I can't remember the exact number, but it's like 10,000 or something. Every 10,000 or so tries is a 50% chance that a randomly selected IV out of the pool of 2 to the 24th power is going to be a duplicate. So by doing it sequentially instead of randomly, we know that we've never had a duplicate, and we also know that when we cross the key space of 2 to the 24th power, that we need to rekey at this point, because at that point, every single IV is going to be a duplicate. Just remember that one thing again. You could say, well, if we don't want to rekey often, can't we increase the size of the initialization vector pool to like 2 to the 32nd power? The problem there is you're reducing the actual key space itself. It's going to make it easier for someone to brute force that. You can increase the size of the key, but then you're decreasing the space for the initialization vector, meaning that you need to rekey more often. If you take a look at something like WPA2, the wireless protocol, that actually creates a transient key based on some master key, based on the passphrase that's protecting it. And that transient key during the handshake that's selected is only used for a short period of time. There's actually an initialization vector that gets set to 1, and then it sequentially goes up, and sometime before it hits hexadecimal, it's supposed to rekey again. And it keeps doing that automatically for you, which is a great improvement from the old web that was out there. And WPA3, of course, you get into asymmetric key cryptography that's used, that we'll talk about here in a moment. There was an attack that came out, probably 8 or something years ago, but it was called the crack attack. And somebody found out with WPA supplicant that you could actually replay, I think it was step 3 of the WPA handshake before the initialization vector pool got exhausted, and it would rekey to 0. So the key would actually become 0. So old Android phones and things like that were very vulnerable to that type of an attack. And that goes back to my point, which is, or one of my earlier points, which is a lot of penetration testers, red teamers, and others avoid cryptography because they're worried about mathematics being involved. But it's usually not the maths that we're going after. It's usually a poorly implemented crypto system because oftentimes the developer of an application or something that doesn't quite understand crypto well enough to implement the crypto system securely. And we've seen that time and time again, proprietary implementations are poorly done. We want it to be, tested publicly and scrutinized before we deem that secure. So hopefully that explains a little bit as to how when we look at symmetric key cryptography, how stream ciphers work. And again, there's always variants of these things, but at its basic form, the stream cipher takes in a length, it takes in a key with or without an initialization vector, it generates a key stream that's then XORed against the plain text to produce the ciphertext. And as long as no one has compromised that key, or you don't have a vulnerability in your crypto system, and you're properly handling and managing the initialization vectors, you should be secure.
That's brilliant.
Alright, so now we're going to switch from stream ciphers under symmetric key cryptography to block ciphers. And we'll also talk briefly about block cipher modes, which are very important. So I'm going to draw here, let's say AES. So that's going to be our cipher, our encryption algorithm. It's a Raindal algorithm, but it's the advanced encryption standard. And before, the cipher took in the key as an input, and it took in the length of the data to produce a key stream. Typically, in block ciphers, the cipher itself is actually encrypting the data using some of those examples we talked about earlier, like substitution and permutation and rotation and others. So let's go ahead and generate our key. I'm going to call E is, we'll just say math. Obviously, we don't have much better than that. And then we're going to actually create some data here. So let's create something I want to encrypt. So I'm going to say I space cryptography. I'll put some exclamation points in there. I want to make sure it's long enough. That's why I'm using those exclamation points. Let's move to that Bitcoin. I don't have any right now, so I don't want it. Alright, so AES is a 16-byte block cipher, unlike DES and triple DES, which are 8-byte block ciphers, which becomes important with things like padding. We're not going to get into padding today. So, since it's a 16-byte block cipher, and it's a block cipher that we're using, we can't have it be a random value like we were able to do with a stream cipher. In a stream cipher, it doesn't matter the length, because the length is an input, and the key stream is generated that's equal to the length of the data that we want to encrypt. In a block cipher, we encrypt based on the block length. So we have to make sure that what we're encrypting meets the block length. And since AES is a 16-byte block cipher, let's see where we're at. So we've got I's at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So right there, I want to put some spaces to separate that. And that's our first 16 bytes. Let's just check that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, then we get over to our second block. 1, 2, 3, 4, 5, 6, 7. So since it needs to be 16 bytes, we now need to add 9 bytes of padding to make it equal 16. Now if this were PKCS padding, like PKCS 7, the number that we would use to pad, or the value that we would use to pad, is the literal number of bytes that we need to pad out. So in this case it's 9, so we would put 9 bytes of 9s, and that's what we would be encrypting. This is going to be our block 1, and over on the right is going to be our block 2. Now as input, we would then take block 1 into the algorithm along with the key of math. So those are the two inputs. Again, it's not the length of what we're encrypting, it is the literal first block of plain text. And what that's going to produce is ciphertext block 1. So if we go up here, we have ciphertext block 1. And that would be something scrambled with a bunch of bytes in it. Pretend that's 16 bytes. Next what would happen is we take block 2 and it would go in with the same key. Now that should already concern you. So remember before we talked about initialization vector and stream ciphers, and that's going to make sure that if the data is the same, block 1 and block 2 are the same, that it's not going to produce the same ciphertext. In this example, to be identical, which is a problem. We want to make sure it's different. You have to alter some uniqueness. Now, there's different block modes that you can use. One example is electronic codebook. In electronic codebook, that's the worst one. It doesn't use an initialization vector, so therefore what I just described is exactly what would happen. Same key, block of data. Same key, block of data. With a different mode like cipher block chaining, we introduce an initialization vector to start making this a bit more secure. There's other modes as well. There's various open feedback modes. There's counter mode. But let's walk through one example, and that would be, let's do cipher block chaining mode, block cipher encryption, to see how we could make this a little bit more secure. So instead of electronic codebook, we can use something called cipher block chaining. This diagram I just put up here is a way for me to explain it and show you how this is a much better option with regards to functionality than receiving mode would be. So at the top, let's pretend that plain text block 2 and block 3 are identical. It's the same. Instead of simply calling that plain text block, now XOR against something. That is something with initialization vector. Let's talk about straight vectors. The important thing here is that the initial initialization vector that we use needs to be created thoughtfully. It shouldn't just be zero, it shouldn't be arbitrary. You should know that it's going to be a unique piece. Alright, only use for the very first block in the
Everybody, click the
say we want to convert something with only 3 blocks in length. The first block of plain text must be XORed against the initialization vector, which is equal to the length of the plain text block. Then being encrypted with our cipher, producing ciphertext block 1.
The link in my bio, that's my new account.
2, which is the same on block 1 as plain text. We don't XOR with that same initialization vector. Instead, we XOR with ciphertext block 1, making it unique as an input into the AES algorithm cipher, producing ciphertext block 2. Then again, with plain text block 3, what we're XORing it against is unique.
Tell Deb she has to end her live and come jump in my box.
What's going in as an input to encrypt the AES is going to be, in fact, unique, resulting in a brand new ciphertext block 3 that's different.
You guys gotta go tell her.
Block 1.
Tell her nice.
This is a great option.
Tell her to end her live and come jump in my box.
Cryptography is speed as well. In this example, we have to run things serially. We can't run them in parallel because we're dependent against the prior operation to be able to continue downstream. But it is a more secure option. As I mentioned before, there are other modes. There are things like counter mode, which does allow you to do things in parallel. There's different types of feedback modes. You can actually combine modes together. And anytime you see something like AES CC something letters, that's usually that it's referring to there. So that's the unique difference between block ciphers and stream ciphers and your symmetric cryptography. And all these things have to be taken into consideration. It's a question where you're assessing a crypto system, or you're performing a risk assessment, you want to ask these types of questions. It's just one example. If you know that electronic codebook is not as good as a block that operates as something like cipher blockchain. Jumping back to the slides, in these examples of asymmetric cryptography, I actually created diagrams that are going to be hopefully easy for us to digest. I like to actually draw them out when I'm talking about symmetric cryptography, especially with stream versus block and the nodes, because I think it's more helpful to piece them together. But with asymmetric cryptography, I think we have a good option here, a good way of going through these slide diagrams that I created. So a couple important things to say first. Symmetric cryptography is a single key system, as we saw. The same key is used to encrypt that we use to decrypt and vice versa. With asymmetric cryptography, it's a two-key system. So in this example, I've got Steve on the left on the bottom, and we've got David on the right on the bottom. Notice that each of us generates a public-private key pair. Now those public-private key pairs are protected via a passphrase that we would then have to remember or enter in to be able to access those keys. typically we are not as protective. Well, always we're not as protective over our public key as we are the private key. You might have heard of something like a PGP key ring, where maybe we have a group of people who work together, and on my key ring, I've got the public key for all the other members of my group, and they have my public key. Because how it works is when you encrypt data with one key, it's pairs, only its other part, which would be the private key in this place, in this example, which would be able to decrypt that data. So if I encrypt with your public key, the only key that can decrypt it is your private key. If you encrypt with my public key, the only key that can decrypt it is my private key. You cannot use the public key to decrypt something that was encrypted with the public key. And the same thing with the private key. That's why it's a two-key system. Now, the key space required to be able to support these asymmetric key cryptographic algorithms are much larger than a symmetric key crypto system. There's actually some good charts you can go out there and Google for, and it will show you. I think the smallest in comparison, meaning the closest in size for an asymmetric key cryptographic algorithm to that of a symmetric key algorithm is ECC, or the elliptical curve crypto system, depending which type you use. Of course, there's Diffie-Hellman, there's RSA, and there's different mathematics as in relation to how it all works. A lot of them use very large factors. We take things like massive prime numbers and we multiply things together, and we get the product. And it's a question about how do we know what numbers we use to come up with that product. I'm simplifying things greatly, but I'll show you an example. In this example here on the slide, though, let's say I encrypt something with David's public key. I send it across to David, across to encrypted. Then again, the only key that can decrypt that data that I encrypted with his public key is his private key, and vice versa. Typically, don't encrypt something with a private key unless we're signing something. We're going to get to that soon. We'll talk about hashing and how that works. So let's look at a quick example with some math. Don't make a horrible mistake here when I'm computing. So this is going to give a little even though I'm going to give you a very basic example, give me an example of how you can solve it. And what we want to do is use asymmetric key cryptography to generate a symmetric key that's going to be used to encrypt data during our session. And it's something I forgot to say. We can absolutely encrypt using asymmetric key cryptography. I can encrypt something with your public key, you can decrypt it with your private key. But that's not typically how we tend to use it. We use asymmetric key cryptography to exchange or generate the shared symmetric or secret key that we're going to be using for the duration of the session. And even on something like PGP, pretty good privacy, when sending messages back and forth, you're actually encrypting a symmetric key with the recipient's public key, and then decrypt that to then decrypt the data. So we're not encrypting the message with the recipient's public key, we're encrypting a symmetric key that they can then use to the private key to encrypt that symmetric key to then decrypt the data that I sent that was encrypted. So it doesn't typically work quite how you think it does in most cases. So again, asymmetric key cryptography, we typically use that to generate or share the symmetric key to be used during a session to encrypt something. So let's talk about how we could potentially generate a key. My goal is for Data9 to somehow generate the same exact symmetric key that we're going to be using to encrypt data back and forth across an insecure network, meaning there's adversaries eavesdropping. So I'm going to simplify this a bit, and again, I'm not a mathematician, but this should work pretty well. So I'm going to say we're going to generate a prime number. So I'm going to say select n equals, and a prime number is a number that's divisible by 1 itself only, right? So I'm going to use 809 for my prime number. We also need to create something called a generator number that is related to the prime. If you want to get into the details as to like how and why the prime and the generator are selected, there's a great articles out there. Just know in this example we need a prime number, which is a number that's divisible by 1 in itself. And the same prime, huge number, and then the generator is usually a simple number that will cover much of the space needed when using that prime number. say choose XA. What this XA, well, actually I'll call it XS to make it more clear. XS is in Steve, so the S is not some fancy math thing, it just means Steve. X is going to be my private value that I never share. So I'll say let's compute XA. Now, I wouldn't normally represent it like this. I would use super or subscript, but I don't know how to do that in preview, so I'm not going to bother trying. I'm going to put F there. S stands for Steve. Okay, this is my private value, and the number I'm going to choose is 9. What I need to then do with that is I need to calculate YD, and D is going to be the public key value that I want to actually send over to David. So I'm going to call YS actually to keep it consistent. So XS is my private value that I'll never share. YS is my public value that I'm going to send over to David. But I need to generate that. So to do that, we would take the generator number, we raise it to the power of my private value, which is XS, and then we mod it to 5, which is 809. So that's the calculation. So I'm going to need a calculator to help me do this, of course. And the number is actually going to be, generator is 733, raise it to the power of my private value, and then mod it to 5. That's the calculation I want to make. Okay, so we want to do 733 generator.
Not at all.
Raise it to the power of
The wood
my
from
private
which it was
value.
made.
And then
For all I know, it comes from a tree that was cut down in the state of Washington. Cut down that tree, it took a saw. To make the saw, it took steel. To make the steel, it took iron. This black center, we call it lead, but it's really graphite, compressed graphite. I'm not sure where it comes from, but I think it comes from some mines in South America. This red topper, the eraser, bit of rubber, probably comes from Malaya, where the rubber tree isn't even native. Imported from South America by some businessmen with the help of the British government. This brass ferrule, I have the slightest idea where it came from. Or the yellow paint, or the paint that made the black line, or the glue that holds it together. Literally thousands of people cooperated to make this pencil. People who don't speak the same language, practice different religions, who might hate one another if they ever met. When you go down to the store and buy this pencil, you are in effect trading a few minutes of your time for a few seconds of time of all those thousands of people. What brought them together? Induced them to cooperate to make this pencil. There was no commissar sending out offices, sending out orders from some central office. It was the magic of the price system, the impersonal operation of prices that brought them together, got them to cooperate to make this pencil so that you could have it for a trifling sum. That is why the operation of the free market is so essential. Not only to promote productive efficiency, but even more to foster harmony and peace among the people of the world. There's not a single person in the world.
We've exchanged the public keys. Now, take a step back. On the internet, or where the adversaries are, they'd be able to see 809 as the line, they'd be able to see 733 as the generator, and they'd be able to see the public values going by. The calculation and the privacy is completely dependent upon the protection of the secret key values on each side. So I'm going to go ahead and write up the next portion of the calculation here. What we're hoping happens now is that we can generate the exact same symmetric key on each side. So we're going to say key, and I'll put S. That's going to be the secret key or symmetric key for Steve. And that calculation is going to be, we take David's public value that was sent across, we raise it to the power of my private value, which is 9, mod it against prime. So that again is going to be 18 raised to the power of private value, mod it to prime, 809, and we should get our answer. So let's go back over to the calculator again. That's 18 to the power of 9. 18 to the power of 9, mod it to prime, which is 809, and we get 315. Let's go back over here. Key S equals 315. That's our symmetric key. What we're hoping is that when we run the same calculation using my public key on David's side, that we get the same value. If we do, then we just shared a symmetric key securely, and we should be good to go, and no one should be able to generate that unless their keys get compromised. So I'm not going to write everything out again. I'll just write the equation we need to do. We need to take my public value, which is 802. We need to raise it to the power of David's private value, which is 11. We need to mod it to prime, which is 809. What we're looking for is JB equals, let's see what it is, 802 to the power of 11, 802, raise it to the power of 11, which is David's private value, and then we mod that to prime, 809, and we get 315. So we see that it works. When you look at that, and I'm sure there's mathematicians, if somebody's watching this who knows math very well, like, oh my god, the way you wrote that out just makes me in a lot of pain, and I completely understand. I'm trying to deal with the limitations of my drawing skills mixed with the app that I'm not used to using. But hopefully that makes sense. Remember, we created 809 is our prime number, 733 is our generator, Steve selected 9 as the private value, David selected 11 as his private value. Those should be protected, never be shared, never be let out, and they're protected via something like a very secure passphrase that gives you access to those keys. Then we came up with the calculation for the public key value in this case that we want to share across the untrusted network. So again, we took the generator, raised it to the power of private value, mod it to the prime number, and I got 802 on my side, we got 18 on David's side. Those get exchanged. We then use those values in the calculation to come up with the symmetric key. So on my side, I took David's public value, raised it to the power of my private value, mod it to prime, we got 315. David takes my public value, which is 802, raise it to the power of his private value, mod it to prime, 315. So therefore, we now have the symmetric key to use for the duration of this session. And there's not many moving parts in that map. I mean, that's again why a lot of times we don't spend our time trying to pen test or assess the mathematics behind everything, because the fewer the moving parts, hopefully the more secure things are. That being said, I think that's a good example of key exchange, which is going to get us to our next part here. So digital signatures. So far we've looked at basic cryptography, we've looked at symmetric key encryption, which is a single key system, and within that we solve block ciphers and stream ciphers. We also then talked about, of course, asymmetric key cryptography and how we typically use that to share or generate the symmetric key that we're going to be using for the duration of the session to have that confidentiality. Because we like to use symmetric key cryptography since it's a single key system and it's faster. We use the asymmetric key cryptography to exchange or generate the symmetric key to use. Then we get into something called non-repudiation, which is how do I know that I'm talking to David? How does he know he's talking to me? If I can convince him that I am who he thinks I am, then I can sign it, and he can then feel confident that it must have come from me. But again, no one's vouching for me. That's when we get into public key cryptography and that web of trust. But in order to understand digital signatures, we have to talk about hashing briefly. So to explain hashing, I'm simply going to go over to a VM, and what we're going to do here is hash a couple things. So if we were to look at our Etsy shadow files, if I say sudo -I and we say hail/Etsy shadow, you can see the user account dead list right there. And then we see this $6. That 6 is the hash identifier. So there's a table out there that tells you which hashing algorithm to use based on that identifier. It could be something like MD5, SHA-1, SHA-256, and many others. Then between the second $sign and the third $sign right there, that's something called a salt, and that value between the $signs, what that does is it adds some uniqueness. It's almost like an initialization vector that we talked about. Let's say that I have the same password as David, and we both have accounts on this system. This hash that's stored here, that's the actual hash of the password. If David's password and my password are the same, the hash stored should be different. And the way we can ensure that it's going to be different is that we correlate this salt value into the equation. So I have a unique salt, David has a unique salt, even though our passwords are the same, when we hash that password, our salts are different, therefore our resulting hash is going to be different. So something that's hashed and turn it back into the input that was sent it in the first place. And I can explain this very easily. If we were to do something like use DD, and I say DD input file equals /dev/VRAM. There's a random there, we'll find out. And we say output file is going to be /10/10.bin, and we say count equals 100, block size equals 4096 bytes, and we use IF. So what I just did there is I created a file of random data that's that size right there. And if I then say, take that file, and we pipe it in into SHA-1 sum, permission denied. Interesting. Let's take a look at that. ls/10. I'm just being lazy and changing that quick here. So if we send that in as input to SHA-1 sum, so what I've taken is the contents of this temp.bin file, and I've sent it into SHA-1 sum, which is a tool that uses the SHA-1 hashing algorithm to generate the message digest or the hash itself. So this right here is a representation of the contents of temp.bin in its current state. As long as that file does not change, or the contents of that file does not change, that hash will always be the same if we run it again and again and again. So it's always the same. But if we were to change one single binary digit inside that file, a completely unique hash would be generated. And it's the same thing if we do something simple, like say, echo the word monkey, and we type that into SHA-1 sum. You can see monkey has the same hash each time. But if you change that to monkeys, it's got a completely different hash. We use hashes for things like password security or password storage. We use it for forensics. So we'll do something like an acquisition of a hard drive image. We'll use multiple hashing algorithms to hash contents of that hard drive image to prove that nothing has been changed, that the data has not been tampered with. We would do that initially during acquisition, and anytime we go to access and take a look at that data, and we show up the ports. So it's proving that the data integrity is intact, that no modifications have been made to the contents of that file. It's a fixed size output. So at the one example, I'm sending in a 7-character word into SHA-1 sum, and it produces that. And in another example, I'm taking the contents of a file that's quite large, and that's going into SHA-1 sum. It's a different value, but the length is the same. It always produces the same length output. Same thing here. If I say echo monkey and we pipe that into MD5 sum, if I can type, and we do it twice, you can see it's the same length. Now notice that the SHA-1 sum is larger now. So if we say echo monkey into SHA-1 sum, see how it's larger? It's a 16 byte to 20 bytes. It's a 16 byte. MD5 is a 16 byte hash. SHA-1 is a 20 byte hash. So that's why you're seeing a difference in the length here. The point I'm trying to make is that if you take a 10 gigabit hard drive image and you send it through the MD5 hashing algorithm, it's still only going to produce a 16 byte output. There's no way to reverse that. You can't take 16 bytes of output and recover a 10 gigabit hard drive, a particular byte hard drive, and it's just not possible. So that's why it's called a one-way transformation that we use for things like data integrity. So I know I probably didn't give the best, most streamlined example of how hashing works. We didn't go into the mechanics of it. It gets pretty interesting, actually. It starts off with these static registers, which then get folded into the algorithm, the one-way transformation. Everything's based on a block size, just like we talked about with AES. I think the block size is 512 bytes. And then if what we're trying to hash is larger than what can fit into a single MD5 block size, we then take the hash of the first block and we use that hash as the registers to hash the second block. And then we do continue on and on. And that's why everything always ends up as the same size at the very end. There's no way to recover anything from it. The only way you can try to do that is if you were to guess what the input was and you get the same resulting hash. Now there are techniques techniques known as rainbow tables that you can use to try to speed things up, and that's why we add salt into the equation. With salt, rainbow tables lose most of their value, but if you're not using salt, something like a rainbow table could actually speed up and determine what something like a password is rather quickly. The reason I wanted to explain hashes, though, briefly, is because this is what we're going to be using as part of our digital signature during that operation. So let's jump back out, and I broke this up into multiple pieces so we can go into each phase. So remember what we're trying to prove now. I'm trying to show non-repudiation. I'm trying to sign what I'm sending you so that you can trust that it came from me or whoever owns that private key. Remember earlier I said we typically never encrypt anything with our private keys. We decrypt something that was encrypted with our public key with our private key. We typically don't encrypt things with our private key. One exception to that is when we want to have non-repudiation in digital signatures. We pay the plain text message. Okay, so let's pretend that this message over here is what I want to send to the recipient. Now, of course, I want to encrypt it with, in this case, we're not dealing with symmetric keys. So I want to encrypt this message with the recipient's public key. And now I've got the encrypted message. I know that the only key that can decrypt that is the recipient's private key. But now I want to sign it, and I want to prove to them that I'm the one who sent the message. And in fact, we can sign things without encrypting it. That's also fine. We're not using a certificate authority in this example. The next thing I'm going to do, and this is why hashing was brought up, I'm going to take that plain text message that I just encrypted in its unencrypted form, and I'm going to run a hashing operation against it. Just like you saw, I echoed monkey from that MD5 and I produced a hash of monkeys. I'm doing that with my message, so we would select a hashing algorithm with SHA-256. I will hash the plain text message, and now I have a hash for that plain text message. Remember, that is data integrity. That's a hash of the data in its current state, and now I've got a hash of that message. The next thing that I do is I encrypt the hash of the plain text message with my private key, and now we've got the encrypted hash that was encrypted with my private key, meaning the only key that can decrypt it is my public key, and we've got the encrypted message, which I encrypted with the recipient's public key. The only key that can decrypt it is the recipient's private key. We send these things over to the recipient. The recipient takes the encrypted message, they use their private key, they decrypt it, and now they have the plain text message. The next thing they do is they take the plain text message that they decrypted, they run it through the same hashing operation like SHA-256 that I used on my side, and they create a hash of the plain text message. The last thing they do is they take the encrypted hash that I encrypted with my private key, they decrypt the encrypted hash with my public key, which produces the resulting hash. If those two hashes match, we have non-repudiation, because that's how I signed it. No one's supposed to have access to my private key, so I encrypted the hash of the message with my private key. You're counting on the fact that no one's compromised that private key. You decrypt the hash with my public key, and you check to see if it matches the hash that you calculate once you decrypt the original encrypted message with your private key. Now, I'll say one last thing on this part, which is we don't have a certificate authority. If I can convince you that I'm Brad Pitt, like I joked around and said earlier, then even though I'm signing it, I may not really be that person. So we use a certificate authority that we trust to vouch on our behalf. We create things like X509 certificates. And basically, we're counting on the fact that someone like VeriSign or Entrust or others have this root certificate authority that's offline, that's protected, has not been compromised. And we can just like I used my private key to encrypt the hash, the certificate authority can encrypt something on my behalf with its private key. Anyone out there can use the certificate authority's public key to decrypt that. So if the certificate authority encrypts using its private key something that I've generated, it's vouching on my behalf. It's saying, yes, I know that that in fact is the right person. I made them show me their ID and all that good stuff. I vetted them. And I am signing using the private key of a certificate authority or a subordinate certificate authority so that when you then decrypt that certificate, that stamp with the certificate authority's public key, and you can check to see, hey, that certificate authority vouched for me. I really am Brad Pitt. You have much more security at that time. Now, of course, the certificate authority can be compromised, so we'd have some really big problems if that were the case. The last thing we're going to talk about in this cryptography walkthrough is going to be steganography, and mostly just because I think it's pretty cool. Steganography, as I explained earlier, is that example where if you came over my house and you saw a safe in the room and it was locked, you know I'm hiding something, but you don't know what the contents are. But if I hide that safe in a wall and I put a picture over it, you now don't even know that I'm hiding something. So it makes it kind of sneaky. One of my first real world, beyond kids using Stego to hide messages from their parents, use cases that I saw, actually there was a couple of them. One was that back when 9/11 happened in the United States and the trade towers were taken down with the jets, it was indicated, but it was withdrawn at some point, so I don't know if it's true or not, that terrorists were using steganography to communicate with terrorist cells. They had a website with a photo of, let's say it's something like Bin Laden, and it's always the same photo, but what happens is the web admin keeps embedding secret messages in that photo and uploading the same photo over and over. So intelligence agencies that are watching that website, they just keep seeing the same photo. But when in reality, the contents of it are changing somehow. And if the terrorist cells know to download that and they use a steganography tool to take out the encrypted message that's embedded in, they decrypt it, they can communicate that way. There was another example in Australia with the Australian Federal Police where there were criminals, I'll just say looking at illicit images, everybody knows what I'm referring to there, they used steganography to hide illicit, illegal images inside legal images. So who would think that someone's hiding pictures and the pictures that are hiding inside are illegal? And it was a law enforcement operation where they were able to determine that these files were steganographically altered, and they used a tool like Stagalizer to extract the contents that were encrypted. Then they try to crack the encryption, the key, to be able to decrypt the contents. So a lot of times criminals are who use steganography. It also gets used by like digital watermarking and stuff like that into the Stego a bit. Now, how does this work? This is one example. There's generation Stego, there's injection Stego, there's replacement Stego. I'm going to use an example called replacement Stego. Now let's say that the message I want to hide is simply the word secret, and I want to hide it in a bitmap image, so like an image of a dog or something like that. Each pixel has a 7-bit binary mapping to it, and that indicates the color. So the first 3 bits in the color mapping, that's going to be your primary colors, like when you're mixing red and blue to create purple, or yellow and black to create some brown. Those bits on the left, especially the first 3 or 4, those are the most critical to the actual color. The bits on the far right, like the lowest 2 bits or 3 bits, if I make changes to those bits, it's unlikely that your eye is going to detect the color change, just because we don't have great vision as humans. Now, if you're looking at some super high-end res photo taken from a digital camera, and you modify the lowest bits, the color is going to be so detailed, you're not going to notice the difference. Now, you could degrade the quality. If you get too greedy and you start taking the lower 4 bits of every 6 or 7 bits, now you're taking too much. You're going to degrade the quality of the image so much that it's going to affect what the user sees. Well, let's set up a scenario. Let's say you're a parent and you take a look at your kid's computer and you see there's a photo of the family dog. That's the only photo you get to see, so you can't even compare that photo to another version that maybe wasn't steganographically altered to see if it's been degraded in quality. So remember that. You don't even know that something's hidden in there. I'm just going to show you how it works. So you can see that we've got secret over there, and I've got the binary representation from the ASCII hex mapper. That's the binary representation of each letter. And what I want to do is hide this data inside this bitmap image without degrading the quality. So of course we'd encrypt it first. We wouldn't just hide the data as is. We encrypt it, but I'm making it simple. What we're doing here is we're taking the first 3 bits and we're hiding it in the lower 3 bits of that 6 or 7-bit field. Now if we go back a slide, it was 011. We changed it to 010. So effectively, we've only modified the lowest bit. You're not going to see a color change that way. Then we go and replace the next lower 3 bits. with 100, and then the next one, and then the next one. So you see how we're hiding the message piece by piece inside the lower bits of each pixel value to not degrade the quality too much to ruin the image. That's basically how it works. It's just one example. Other examples, we can hide it in Slack space and stuff. There's all kinds of things we can do. But that's pretty sneaky, right? How you can go in, encrypt a message, hide it in a host file. This could be an MP3 file if you want. If you take an MP3 file and it's 256-bit quality, kilobit per second bit quality, and we reduce that to 192 kilobit per second bit quality, most people would not detect the change in the ears when in fact we're now hiding data in the lower portions of each of those sections of data. So I think that's actually, Dave, at the end of what I wanted to talk about here. I know there's a lot of information, and I know some parts are smoother than others.
I think it's great. I think a lot of people might be more interested in hashing. So I think just for everyone who's watching, please put your comments below. Do you want more hashing detail? Because I think, Stephen, I've seen so many misunderstandings about hashing. So perhaps you can do like a detailed one on hashing.
Yeah, I think one thing we could do is take a look at hashing in more detail. Maybe not go into like the depths of how the algorithm and the math works. We can put up an image that shows you like the registers that are used, the initial block size, how that factors in. And we could use that to talk about something like hash length extension attacks and actually see an example of how you would go and go after an implementation that's insecure.
Maybe like pigeonhole, stuff like that, if you'd like to cover that.
Yeah, we can certainly take a look at anything.
Yeah, that'd be great. So just for everyone watching, please put your comments below. Do you want to see more about hashing? But Stephen, I really want to thank you for putting this presentation together. I mean, it's a lot of information. It's like a full tutorial that we get for free. So I really appreciate you doing it. Yeah,
thanks. It's hard to pick what we're going to talk about with crypto. So I tried to pick some sections that I know that are like very common out there. And again, when you're trying to take on a topic like crypto, you don't quite know each person's level of mathematics and where they lie. So I'm trying to simplify things in such a way and show you examples without getting too complex on things so it's digestible for folks. So hopefully I didn't mess that up too much and you get some value from it. Feel free in the comments if you want to pickle me about my math skills or my drawing skills. You're not going to hurt my feelings. I have no ego. I'm not trying to say that I'm some brilliant mathematician, but just wanted to shed some light on some cryptographic issues. And also, if I made a mistake anywhere, let me know. I'm happy to correct that as well. But I think I got through everything, but sometimes it's hard to not miss this wording somewhere.
And just for everyone's benefit again, can you remind us about your YouTube channel?
Yes, thank you. It's Off-By-One Security on YouTube. I do streams every Friday. I have a lot of guests. Like, obviously, I don't know when this video is getting posted, but I'll just had Chomsky on. I just had just a lot of amazing folks who share their knowledge on fuzzing and how they approach vulnerability research. And then, of course, branching out to different things like web application security, crypto, and blockchain, and smart contracts, and just all over the map. So I also have a Discord server that you can check out. And it's an open one. There's a couple thousand members right now. Very friendly community, but I brought that up because there's a channel on there for requesting streams and requesting certain guests. And of course, I can certainly try and accommodate that if possible so we can cover topics that you're interested in.
So for everyone watching, please go and show the love. Go and sub to Stephen's channel. He's trying to grow it. Stephen, again, thanks so much.
Yeah, thanks, David.
So this is Zerodium. It's an example of a company out there that will pay up to $2 million US for iOS exploits. You do have to think about who is buying that, who will end up with that exploit, how powerful it is. That's the type of money that you can make. And this example here came out on Twitter recently where it's up to $20 million US. Mind-blowing. The payout amounts at this level, you're often selling it to those same nations who are potentially using to attack your own government, which is not such a good thing.
Hey everyone, it's David Bombal back with the amazing Stevenson. Stephen, welcome.
Thanks, David. Good to be on again.
It's great to have you here. Just for everyone who doesn't know you, I mean, you're absolutely amazing. One of the authors of this book, Grey Hat Hacking. You've also created a bunch of what I would say insane, difficult courses of science. You've also got an amazing YouTube channel. So just for everyone who's watching, before we go anywhere, please go and subscribe to Stephen's channel. I always get pushback on YouTube. David, you make content that's too simple. Well, if you really want some hardcore hacking content, sort of insane good content, go and subscribe to Stephen's channel. Make sure you go and sub. But Stephen, Steven, perhaps just for people who don't know who you are, tell us a bit about, what you've been up to for the last 20 years and, the kind of courses that you're creating at SAM.
Yeah, sure. It's my third time being on the show with you, so it's great to be back again. Yeah, so I've been teaching for the SANS Institute for probably around 15 years now, which I would say is impossible because I'm still in my 20s. I've been an author as well, like you said. I've written some courses or contributed multiple courses, mostly on export development and integration testing. That's really where my heart is diversity and exploitation. It's one of those things that I'm sure you agree, the beauty about information security in general is there's so many facets or areas of it where you get bored and you move on to the next one and you don't want to be the smartest person in the room. There's so much to strive for.
That's exactly right. I mean, that's why I love talking to you and other people who've been doing this for so many years. And I believe you've got a really exciting presentation to share.
Yeah, actually, I think the last couple times maybe I shared my screen a little bit, but the topic we're going to go through today, I felt is maybe a little bit more formal presentation. Aside from the SANS thing, like I'm working on some products and building those out. As you mentioned, the off-island security channel has been really great. I just need to make sure I stick to doing it every Friday. Sometimes my guests, they don't show up, and then I have to do something ad hoc. So it's great, and I'm still doing a lot of exploitation and zero-day bug hunting. The beauty of all this new technology coming out is even though it's getting a lot harder, or it is a lot harder than it used to be, and I'll mention that in the presentation in this session, there's so many new attack surfaces out there that you're going to find something. It changes.
Yeah, I like to highlight, you're very humble, but the courses that you've been creating at SANS are like really hardcore, high-level courses. You go into the nitty-gritty stuff that I don't understand. But I think, for someone who's starting out in 2024, what do I need to do to become like you? I think is the big thing that a lot of people would be interested in. If I'm starting out, I want to change careers, or I'm young, I want to get into this stuff. Do you have like sort of a path that I can take to, get to that kind of level?
Yeah, so in the presentation, I've got this one specific slide towards the end that kind of says a beginning and an end, and there's going to be a lot of topics on there, or a lot of things on there that you can do to really improve your chops, improve your skills. So much of it is a lot of sacrifice, but there's an important part of that, which is you still need a social life, you still need to have friends and all these things, but so many of us have given up so much to get where we are today, and you're not going to find too many of the greats out there who haven't made a lot of sacrifice. So it definitely is just like learning a new language, like French or Japanese, like it takes a serious commitment, and it's a lifelong commitment.
That's a great warning. I mean, it's you don't become the best at anything by just sitting around watching television.
Yeah, the amazing thing is we just had a conference. So I was the chair, or one of the chairs, of the conference that we had last Thursday and Friday. This would be in November in 2023 in Los Angeles, called Hackfest Hollywood, and it was a blast. And part of what I want to do, and what you're supposed to do if you're a teacher in general, is you want your students to become smarter than you. Next generation, they're supposed to improve. Same thing like when you look at Tony Hawk. Come out, they're like doing the stuff he was doing 20 years ago with ease, and same thing like this hard playing. You see the hardware these days compared to the past. It's just amazing to watch, and so like the reason to bring that up is I invited one of these people who I consider to be the next generation amazing hackers, and they already are. People like Charles Beavers, Valentina Milioti, and Lena Lau, and Connor Mazar, and Ruben Zunin, and folks like that. They're all late 20s, I think. They're early 30s, but one of them was like, some of them have been doing it for 5 or 6 years, and they are already at or beyond my level in some areas.
I mean, it's great. I mean, the story leads. It's great. Make those short goals. I fully agree with that. Do you want to jump into those slides, Steven?
Yes, I made it official with the proper slides at this time, so I didn't know what to call it, but there are some questions
driving naked for a
and it's always how do I
she said she was
how do I get to the next level, and a lot of people complain about me being like,
oh, yesterday found another way, oh, yesterday synthetic one way, oh, the other, 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 oh,
No, it's great, man.
Ways to quickly progress and profit in the world of hacking. There's a YouTube channel there and a Twitter handle as well. So this certainly is not all of the areas where you can earn money by hacking. These are, I would say, three of kind of the big groups that I look at. Starting on the left would be cybercrime, which I'm certainly not going to advocate for that. But people do make money in that path, and I've got a funny story on that specifically. And then bug bounty disclosures. It's a huge area, and you see people all the time talking about how they got a $300 bounty, a $3,000 US bounty, and beyond that, I think it's funny. Like you'll see, there's a no hackers. The younger people always put their age up there, and the older people like there are just so many. agent thought that
It's been said that that you work when you're working, you work when you're on the road. You carry studio around with you. You get up in the middle of the night. You get an idea for a tune, and you get up and go do it. From Detroit.
And you could actually buy an instance of it on the dark web and profit. And what you see here on the screen is similar to that, where we have one called Satan on the left, and on the right is just another example of Bitcoin. How to blackmail for Bitcoin Academy. And if you look at the details down there, find me on AlphaBay. That's an old marketplace that I think was shut down by law enforcement, but new ones always pop up. But it says, hacker hold Hollywood hospital to ransom for $3.6 million in Bitcoin in ransomware cyber attack. And then the note, this is the author of this ransomware course saying, what if you was that hacker? I bet he was just 16 years old kid in the right place at the right time, just like you are now. And it's like, Carol's death fountain, it looks like money can solve all your problems. I mean, look at who they're targeting, right? They're clearly targeting young folks who, hey, you want to be able to play Fortnite and make some passive income on the side. Buy a copy of my ransomware. What you end up getting in there is the way it's often written. You'll have a Bitcoin wallet or a Monero wallet, and there might be two wallets. One wallet is
it's an art to max that beat to 11 like Elvin and Jack pretty rhythms within him. Bang, I'm a Candido like Tito, a roll off the Richter like Eddie, swinging, sunning and budding, rocking the steady. It's that beat, it's that beat, it's that beat, it's that beat, it's that beat.
Your job is just to get it out there and lock up people.
It's that beat, it's that beat, it's that beat.
Anyone wants to unlock the computer,
it's that beat, so sweet.
Then both of you make money. It's quite an interesting business model, and as you can imagine, it's probably pretty successful. I mean, the challenging part for the person who doesn't really know what they're doing is getting this ransomware onto a computer to lock it up. So a lot of times people will package it up with some type of a worm to be able to go out and try to automatically infect computers, which is obviously going to get you a lot more money.
The problem is one day they're going to catch you, right? Like so many of these people.
Almost always people get caught. I mean, I don't know, look at the recent examples of MGM.
Moving bods like dog piles and play, bad like Gladstone, Egad, Sun and K. Those shimmy flam hits from chick skip with a brush to the tip. Hats to top troopers like Kruger and Flip. It's that beat, it's that beat, it's that beat.
Some casinos pay some heck.
It's that beat, so sweet. It's that beat, it's that beat, it's that beat. It's that beat, so sweet.
How much money are we losing?
It's that beat, it's that beat, it's that beat.
Versus how much
it's that beat, so
then again, as we all know, if you pay the ransom, then our company has more money.
They might not unlock it anyway.
Right. And sometimes, like some examples, depending on the way in which the key is working, the key that was used to encrypt your file system or files on your file system,
God made Clark happen, and amen for Atlas. Around the world like Moon, bombing like Bono. Poncho and Mongo taped up, slapping skins till it hurts. Double kickstart hearts like Jones, Star and Hurt. It's that beat, it's that beat, it's that beat, it's that beat,
the key management is going to be more complex, and he's going to be stored somewhere else. And if
it's that beat, it's that beat, it's that beat.
Even if you pay the ransom,
it's that beat, so sweet.
I didn't want this to be a ransomware talk for sure, but I wanted to point out, look at the bottom left there. AI has made this even easier.
It's that
cross
beat.
out if once you can get past the generative AI prompt protections. And I've got an example to show you on the next one here. So this is one slide in a set of slides that I did in an RSA talk earlier this year. So I just wanted to pull one slide from that presentation to point out to you kind of what's happening here. So back when ChatGPT became available to the public in November 2022, one of the first things I had to do is I wanted to write this code. One of the programs I wanted to write just to see if the code said write the interesting moment there. And I said, hey, I can tell what they were doing from the code. And I was like, oh, you're working with some experimentation or something. Like, oh, how do you know that? So we got to talking. And they were telling me that they, and some of the friends of theirs in Moldova, there were no opportunities at the time. I think this is very good for the but at the time, they said that it was really hard to get well. Cyber was they will pay us. And my point earlier was, now that there are these bug bounties accessible to anyone in the world, that darker path may not be there. It'd be harder to argue that I didn't have opportunity.
Yeah, it's a good point. Good point. I mean, it's fantastic how it works.
Absolutely. So let's jump into the get out of the dark area. We can spend hours talking about that. It's fun, but so let's not do this. This is one of the big ways in which we make money. There's a lot of competition, a whole lot of competition. I almost said a better note, don't say it. I'm coaching myself. But just think about other things that have a lot more competition now than they used to. Like, so it's harder to make money when you're so many people, but you should be able to stand out. So let's talk a bit about this. I like to look at it where there's two primary categories, even though someone's going to argue there's way more than that, and I agree there is way more than that, but these are two that I like to look at: binary exploitation and then web application exploitation. And yes, there are others. You can go after routers and whatever, but on the left, this is a state. It's a few years old now, but I still like it as a visual art. I got this from Matt Miller, who works at Microsoft, and it's basically the root cause of remote code execution vulnerabilities that were discovered and disclosed to Microsoft by Patcheater. You can see it only goes up to 2017, but it's all color coded. And look at the changes. And like one thing I'll point out that's interesting to me is, right, I don't know if you can see my cursor, but right there in the middle where the gray big gap is, that gray maps to use after free. Use after free was at its peak in 2014. And then it started to get closed down. There's an interesting reason as to why it started to get closed down. If you remember back then, if you were around and doing this back then and dealing with patches with Microsoft boxes, you would see, or you would have seen, that every patch Tuesday, there were 20, 30, 40 or more vulnerabilities getting patched specifically in the Internet Explorer. It was just not doing well. And they were all use after free, some patching using as well. Most of use after free. Microsoft in 2014 in the summer dropped these two mitigations called MUC or deferred free, and then also isolate. Those mitigations were so powerful in the browser that it pretty much stopped us from being able to exploit those vulnerabilities when we find them. So those vulnerabilities are still there, but you can't exploit them because it's and the problem with ours is
Vero, 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 vero,
hackers out there. That's a little bit about what I want to talk about, because going into this, you kind of have to set yourself up and be realistic about your expectations and really understand how much work you're going to have to put in. And at some point, you got to determine whether or not it's the right spot for you. I don't want to be something that you don't want to hear, but if I want to go and become a professional snowboarder, probably not going to happen. Probably not going to go to the Olympics. I was in my 20s. This is an area that's more accessible to that. It's not the same thing. But you know, there's nothing wrong with that. If you find out that you're just not enjoying yourself and give it a go, there's so many areas you can explore. So what about this is not many of them, though, and I'm sure if you've watched kind of Twitter, X, whatever it's called, and watch what people say, some of them are not much money, $200, $400, $500, and that's fine, but you're going to have to do a lot more. You're going to have to find a lot of them to be able to make a good living, and it's something that's inconsistent. I'll say that a couple of times in this section. It's not like working a 9-to-5 job, 40 hours a week, whatever it is, and you can count on that paycheck coming in. This is very much, you might have a really good month where you're eating the fancy restaurants, and then the next month you're back to McDonald's. I'm not great with finances, but I will say absolutely put money away as early as possible. Don't go blowing through all of that. I know it's fun to go out there and buy the Lamborghini. You saw the crypto person did, but there was this old movie called Dave Boy. It's a really great movie about some folks in the inner city, and I remember, I think it was Dave Raines, who's the actor. He's talking to these younger folk, and he's saying, you guys are stupid. You guys spend all your money on clothing and jewelry and all this flashy stuff. It's like, it's guns and butter. It's like, your stuff you're buying is butter. You gotta buy the guns, the property, and the bonds, and all that.
Right.
Instead of appreciate, not depreciate. But, so, major players, you've all heard of HackerOne, Bugcrowd, Synack, maybe not as well known, but those are three of the biggest ones out there. And there are hundreds of thousands of them. Now, I will tell you, most of those, because they're members of the most of them are local, and they will find something that, one thing you'll run into, and I learned this from a coworker of mine, he's a really great Bugcrowd guy. He's found a lot of owners. 1, 2, 6, 7, 8. And I learned from him that duplicates are a serious challenge in the world of web apps, where you go and put something in, and then they come back and say, this is already found by 5 other people, and you're not going to be paid for it. And that can be frustrating, but really use that knowledge that you gain from finding that to go and find another one. And I'm going to say this in a slide or two now, but I want to say it again now because it's really important, which is one of the things I learned from really good web app Bugcrowd folks is that watch the website and just hold it. Do this again. Watch it, because when they make a change to that website, the attack surface may have now changed. And you want to be the first one to identify that change and check to see if it could be a new opportunity. They, being the people who are smarter than me with Bugcrowd stuff in the web, have told me that that's just been a big help for that. It's not many people are doing that. There's a lot on it. It's not really it could be. But there's a lot of competition. I mean, when you see videos like from Ben or Namsek up there on the top right, great guy and great videos, when you tell the other people, I made $100,000 hacking. That's gonna raise my alarm. It's gonna get people to jail, it's gonna swag, that's good money. Look at the bottom there, HackerOne. remember dating this girl way back when I was a teenager, and she also was a teenager. I think she was like 14 or 15, I was the same. And I had been playing piano for a few years, wanting to become a good keyboardist, and I suck, for lack of better terms. It's a thing with darts. I've been playing darts my whole life, and I hit a point where I just never got any better. I can't get any better. I hit my peak, and that can happen to us. So you gotta, be realistic if you do hit those peaks, but don't let it discourage you, because so many of us, including myself, have had to work through where it's almost like you're trying to lose weight and you hit a plateau where you lost 10 kilos, whatever, pretty quickly, and then you're like stuck there for months. Keep going, right? So that's just something I wanted to point out there. All right, so jumping into binary exploitation, the amount of money that you can make in this space can get really big. And we'll talk about how big here. If you watched the episode when David and I talked previously, you might remember this slide, or you may have seen this slide or this information elsewhere, like on the Zerodium site. Now this is the bounties that they, Zerodium, will pay up to depending on what it is that you find. And if you look at the two sides, the left is mobile devices and the right is like desktop servers. And the applications, if you look towards the middle, you can see things like iMessage, Signal, Telegram, Chrome, Safari, Adobe, WinRAR, 7-Zip. Like these are big applications that we all use. And it's funny because I get people a lot of times who will send me a message on Twitter or email, and they'll say, hey, I found this vulnerability in some random FTP server that someone wrote in 1994, and how much money is it worth? Like, it's not worth it. It's not worth anything, but good on you for finding it. Like, you definitely learned a lot doing that. Keep going. But if you want to know what kind of apps you will get paid for, this is that. But think about who you're selling it to. I will talk about this again in a little bit. There are different types of buyers out there. There are ethical buyers. There are the vendors themselves who are affected by your discovery. Then there are intelligence agencies who will buy them in nation states. And then there's just, going into darker places where what they are going to use that exploit for could be just no good. But we'll get back to that. Zerodium is an example of a company where you don't get to know who their customers are. So if you sell them for $2.5 million an Android full chain persistent zero-click exploit, then think about who might be getting that. If they're willing to pay $2.5 million, what are their customers paying for? So morals come into play, your ethics, all that fun stuff. This would not be an example of responsible disclosure, but I do list it because there's payouts. When you look at this, and unfortunately, the vendors themselves, like if you found a vulnerability in Adobe Acrobat Editor, Adobe's not going to pay you as much as what. So a few months ago, if you look at this slide, it came out on Twitter, September 26, 2023. This tweet appeared, and it says up to $20 million for what Zerodium would pay up to $2 million for. And this is specifically iOS, so iPad, iPhone, full chain, zero click. Now, what that means is typically these are iMessage vulnerabilities where the parsing of an SMS or text message that comes into your device, that initial parsing sort of the Pegasus malware and such, and that's like the malware that gets installed once you are able to exploit the phone. It's kind of like what you command and control kind of presence on that device allows you to do crazy stuff, like turn the camera on, turn the microphone on, take documents. But you don't see them coming out anymore because it's so hard that the research that the people are doing, the groups of people are doing, hold that information very close to the chest. I don't know about you, I think it's higher than that.
Exactly. It's interesting. I interviewed some of the Cisco Telecom team, a few people, and they were talking about this rise of credit. It seems like this is definitely a rise.
It's definitely an area that going back to what I was saying earlier it's similar to how I said this already, if it were easy, the payouts would be so high. It is a very challenging path to go down and typically very inconsistent. By inconsistent, I mean what I said before, where you can eat well one month and the next month you try. You don't have to go for the big prize. Keep that in mind. You don't have to set your eyes on the iOS exploit. Honestly, we're up against some real talent, multiple people, well-funded, and it's very hard. So starting smaller, there's still plenty of opportunity to make a lot of money. I'll look at it a little bit. Identify the attack surface that you haven't seen much research on. And by attack surface, I mean, like, I remember Kyle Gorman was doing a Project Zero years ago. He just tweeted out one Friday, I don't have anything going on this weekend. I think I'll take a look at the NTFS driver. Now, if you're at Microsoft, you don't want to hear that guy. But like, that's an example of an attack surface. And if you haven't seen anybody else really open on that attack surface, like years ago, fonts, those were very often looked at. And fonts are supposed to happen in the front. And so if you're trying to be vulnerabilities, like vulnerabilities like that, it's going to result in zero code. That ended up being one of the
like Iceland. Personally,
so identify an attack surface. It doesn't have to be anything crazy at first. There's another area related to binary exploitation. It really is binary exploitation that you can make good money. It's not going to be as lucrative as 0 days if you were able to find them, but this is going to be something that's more absolute, I guess maybe a right word to use, where there is a guaranteed ending if you can find it. Like if someone hides a gold coin in the woods behind your house, you know that you're looking for something that does in fact exist. Versus if you don't know if there's a gold coin out there, you could spend years and you're never going to find it. So that's kind of like 0 days versus end-day exploitation. End-day exploitation is, we used to call it one-day exploits. It used to be Patch Tuesday, Exploit Wednesday, the same. And the idea there was when Patch Tuesday started back in like 2002 or 2003, the second Tuesday of every month, Microsoft patches come out, and you could take the patch, extract it, take the file that was patched, and dip it against the unpatched version of that file. And what should stick out pretty obviously is the changed code, which then allow you to find out what the vulnerability is, and then try to see if you can create an exploit. Now, it's easy to do that part. It's really easy to dip and to identify the code changes. It goes up from there in terms of difficulty. So easy part of extracting, identifying the code changes. The next step up is understanding what the vulnerability is. Just because you see code changes doesn't mean you're going to be able to process what the vulnerability is. Then the next step up is debugging, setting a breakpoint on that function that contains the vulnerability in the unpatched version, and then trying to get to that line of code. Sometimes it's easy, most of the time it's pretty hard. Because think about what you might be looking at. Maybe you're looking at RPC code or Microsoft Terminal Services code, and what you're looking at is some weird little compression function that is nested in there somewhere, and you don't even know what compression it's talking about because maybe the symbols aren't there. So you've got to search around and around and keep messing with it to sometimes write your own client. Eventually, if you get to that breakpoint, like you pat yourself on the back, you did something. Like I remember one time I spent over a week just trying to get to a breakpoint that I set. Once I hit it, it's usually just when I'm about to give up is when I find the little carrot gets dangled. I was excited. I opened up the beer. I was proud of myself. I made it. But then you've got to figure out how to weaponize that thing and get code execution. You might have to do heap grooming and all kinds of crazy stuff. You might have to tie it together with also an ASLR bypass. It's tough, but with end day exploitation, the end being the number of days it takes you to be able to weaponize this thing, sometimes you can't weaponize it. Sometimes it's just not possible. Some things are patched that are more theoretical, where even though it's highly unlikely that someone could exploit it, or even though the mitigations that are on by default are protecting it, they're still going to patch it. So what you find may end up being very frustrating because you realize at some point that you've been wasting your time. You really haven't. You shouldn't look at it like that because you've learned a lot along the way. Now you might be better at RPC, for example. But on the good side, if you are able to weaponize it, then think about the power you have. Like it says on the slide, over 90% of vulnerable disclosures are private. That means all those CVEs out there, most of them, almost all of them, there is no corresponding exploit public. Think about the power. Like my little example there, I say, you go insert your exploitation framework, like I don't know, Steve something, and that was your product. And now what am I really talking about? Metasploit, foreign hack, Sync exploit, Canvas, there's other ones out there. These are these exploitation frameworks. Most of us are using Metasploit. And if you can say to your customers, you have, this number up, thousands of working exploits against privately disclosed vulnerabilities, your product is going to be very desirable because most organizations are terrible at patching. So the faster that you can weaponize a patched vulnerability, the more value it's going to have. It's a bit of a race condition. Most orgs take weeks, if not months, if not longer to patch. And even if they say they patch, they might not be patched completely. And that like when you saw in the scenario, you're a red team, right? The red team, you're uploading this target, doing some service collection, OS fingerprinting, whatever you want to call it, identification of the services, and you then look up in your little spreadsheet in your tool, and you see that you've got weaponized exploits against privately disclosed CVEs, and that target is not patched. You have a power that no one else in your position would have because you're the only one with an exploit to that privately disclosed vulnerability. Or imagine you're a red teamer, you're looking at a super lockdown environment. Red teaming is getting harder and harder as it should be. And you see Patch Tuesday just came out 2 days ago. You look at the list of patches and you see that the organization uses a couple of those services or whatever it is that's patch drivers. If you've got somebody on your team with the power to be able to weaponize those patch vulnerabilities, that might be your way in. There are groups of people sitting around doing this all over the place in every category that you think of. Meaning category like well-functioning a vulnerability against 7-zip or WinZip and something else out there, if you could weaponize that vulnerability and quickly, there's a price tag next to each one. Some of them were pretty high. Some of them are like $20,000, $30,000 US that you could make by weaponizing this patch vulnerability. So it is a thing. I used to know a guy who every quarter Oracle patches would come out. I don't know if Oracle still does it that way, but it used to be every quarter. And he would do diffing and find vulnerabilities in Oracle because nobody patched Oracle at the time. Very powerful. And the last example there at the bottom, like look at the success of weaponized exploits against patch vulnerabilities in the past, right? Config was a thing. It was years ago, but my point of saying that specific one is that there were several months that went by after the patch had been available before this thing came out, and it was still really successful. How can it be successful if the patch has been out? Demonstrates the problem. So this one here, what is the patch level in the target organization? This is a little Microsoft visual that I pulled out of a presentation they put together a while ago, and what it shows is that a PC in a typical enterprise is on the left, selectively patched, versus the one on the right, which is what Microsoft uses in their labs. Microsoft, they're going to test against a operating system that's fully patched up to date. As where on the left is a typical organization where, look at the very bottom right, the little square, right on the very bottom right. Let's say that that's this month. That represents patches in November 2023, or it's January 2024, whatever that is. You see how some of them are missing? Like, if we said, like, this grouping right here are the patches from that month, a few of them are missing. So the admin might say, we are patched up to date, but you are missing some patches because you decided not to roll them out for one reason or another. Maybe it's a broken business process. Like, simple example, I use Pro Tools a lot, and I've got music equipment that connects to my Mac, and I get alerts all the time that says, do not upgrade to the newest Mac OS version that came out because it will break this music like your audio. So there are reasons why you can't upgrade. And that's why, like Microsoft, if you go to turn on your Xbox, you have it turned on, mandatory patch. You don't have to get signed out because they want people to be working like the bottom right there. So the point of this slide is to say that you see the value in these patch vulnerabilities out of the you never know. You'll be up against the target organization.
That's a great slide.
This is a silly example I've used many times, but QR codes. And the joke is, can you spot the difference between the two? Like, it depends on what we're actually doing. Come on, chat! Fold it right there, nigga! Fold it, instant fold! It's one of those black little squares is a function or code within a function. If you were given these two samples and somebody said, find the one block difference between the two, it's going to take you a while and it's going to be really annoying. You'll be able to do it, but it's going to take you. And then if you go forward, well, there it is. Obviously, it is the black square missing the crap there on the right. And when you think about a real Microsoft DLL, sometimes there's 50,000 or more functions in them, and each of those functions has blocks of code within it. Each of those blocks of code has assembly or machine code inside. So it is it's quite the undertaking if you don't have diff tools. So what does a diff tool do? This is a silly example of two functions. Basically, these are blocks of code within a function. The one on the left is unpatched, the one on the right is patched. It's the exact same piece of the exact same function. And you can see on the bottom that there's a different colored block and there's actually...
Oh, yeah. Sharing the theory, don't you know that?
Eating ass on the first link.
I'm eating it.
There's an instruction that says move the value 1 into the accumulator register. But on the right,
but I haven't seen anyone make it.
Your job would be then, this is what I was explaining or describing earlier, is how
it seems like everybody moving out of hand. What the fuck are you talking? What do I do? I'm having a square.
That line of code
That's what it seems like everybody moving out of hand. What the fuck are you talking? What do I do? I'm having a square. What do I do? I'm having a square. I don't even do that. What?
About RPC, you have a whole lot of sometimes you're going to find somebody else's client, leverage that.
There's a new Gatorade. There's a new Gatorade. There's a new Gatorade card. There's a new Gatorade card. Why Cayenne with the 5 gifted appreciated? Why Cayenne? Tomorrow! Yeah! It's the tomorrow! You wake up tomorrow! Yeah! Tomorrow you wake up, you motivate tomorrow! Yeah! And you tomorrow! Yeah! Tomorrow you fucking wake up and you go to tomorrow like
under the specification RIFF, the resource interchange file formatted data, and it's a subcategory of that. And then you just study, you have to structure it. Then you have to write your own editing structure and try to figure out how to get to that line of code. So it can be very time consuming. But as you can see, the diffing tool is going to speed up your wake up! Yeah! Wake up! So we do it tomorrow!
After school. Nah, the worst shit is like when you about to shit and it don't come out. Yeah, no. Nah, I really don't like diarrhea. I don't like when it shits. It's really just pushing it come out. Out of that mode. No. That's just like with the dookie, like stretch your butt and stretch it. Nah, what? Nigga, I know.
For us there,
that was crazy, Ricardo. You really took your chin.
This is the book.
Yeah. Bro, hey! Bro. What's the New Jersey thing I missed? Yeah. Bro, hey!
Wind Index. Wind Index is a site.
No, this picture is fire!
There's every single patent that comes out all these without you don't have to know. And manually do the extraction. You don't want to do that. So they did.
Oh my god!
Against the unpatented version.
These are making say, bro. It's important to like small streamers, bro. Get a culture, bro. So you got like this is a good experience for you. You know what I'm saying? I'm his favorite streamer. So.
American Daddy Taro with the 5 get the picture. American.
This is fire. No. He's 15. I know he feels so happy right now, nigga. If I was him, I would want to be that too.
A lot of hard work. One last time I'll say it. Single-handedly, if you like I said, you are a big value to whatever company you're working for. Special. So in the rest category, there are other categories like I said, but this is professional services. This is where most of them start. There are some people out there that see people all the time. Again, they're middle high school. They're fighting web bug bounties. It is so different from there's so many people coming into the space now, starting so early that security is way better off. So this is going to be a fun trial here.
Why do you think it's dead? He was thinking it a little bit too hard, man.
So around 14 and a half years old, I wanted to be able to buy it for the things like so when I was working at McDonald's, something happened there that really piqued my interest. There was this kid, I was 14 and a half, this guy was like 7. He was at the same high school that I was. I remember he was getting a nerd or whatever back in the day. It was a bad thing. Simply not a bad thing. I ended up working hey, I noticed you're on the computer a lot at school. What do you do? Program. And I was like, oh, you program. My dad's a programmer. He's like, here we go. I was like, oh, what are you working on? He's like, I'm working on 14-year-old me at McDonald's, like, what the hell is a polymorphication? He was writing viruses. Like, he was one of those guys. And that was kind of my first. And at the time, my dad actually brought home. He was working nights. Databases. We had a computer at the house pretty earlier than most people. Most of my friends. Talking about the late 90s. So dialing up your modem, the whole thing where modem plays your authentication or admin. Like, that was a thing. That is not hard. back working at Wells Fargo, if I'm back working at Wells Fargo, and on the side, I write a Windows 0 against Chrome or Edge, and it results in low code execution, and I just pop it up there on XP, don't tell Microsoft about it, and use my name, or I Google that a lot of people kind of find the name right away. You're outside the country, you don't know who you are. Meanwhile, people are like, why is this guy who works at this company releasing 0 days that affect my company? That's not a good look. So I have a couple handles out there which have quite a few, but honestly, personally, I've never been one to care about getting POC. I think it's because of my age that I started. I always want to be engaged in my research. Driving me talking about it. She said you were almost a master. Yes, it's just never been. Party yesterday, on another way. Party yesterday, synthetic one way. All the other, 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 all the other. Looking back at what I was just describing, a joke with my wife before, like, just make sure there's no black van parked outside the house. That is, it's funny, but it's not a joke, because this is another thing, and again, I don't want to, like, act like I'm telling people what to do, or to make their own choices. I'm trying to say, based on my experiences, what's worked for me, some of the dangers that I've seen out there, I have seen get too mouthy, too chatty, too ego around things that they're doing and finding important things. Think about the intention. I don't think there's any conspiracy theory. Question, but I don't think there's Barnaby Jack was a film actor in Australia, lived in San Francisco. too long. You're gonna go through a proxy. I'm not gonna name any of the proxies because I did that before. They good people. They good people. The student came right up to me the first time. He said, "How did you know that my company buys that?" And I was like, "Okay." So that's not the thing. There are, I'll just say, there are companies that are proxies on behalf of governments that live in various countries who will buy.
It's been said that you work when you're working, you work when you're on the road, you carry your studio around with you, you get up in the middle of the night, you get an idea for a tune, and you get up and go do it. From Detroit.
Bro, I know how you live. That's why I'm saying. That's why I wanted you for the show, because you kind of got that. You know what I'm saying?
Available to do that. I sold it for $120,000, and that's a lot of money, right? But I said that in front of the class one time, and this guy came up to me. He's like, "I work for a company." The
15? Nah, y'all be turning up. I know how this is. Where'd you guys go eat at? Damn, where's this at?
Yo, I'm Hollywood.
They have desserts too and everything?
I've been hearing about that, and I'm like, I'm not being out on my
Why y'all be like that though? You know what I'm saying? Let us take you out one time. Are you? Pisces, obviously the whole year. What is it? March, February. Oh, we are February Pisces. Okay, see, I like moms though. Moms know what's up. I'm March 13th. I be turning up.
Pretty rhythms within them.
So you getting here is okay?
Bang, I'm a candida like Tito. A roll off the Richter like Eddie. Swinging, sunny and buddy, rocking.
It's like literally a mini White House.
It's that beat, it's that beat, it's that beat, it's that beat.
I'm starting to film over here, so this will be my main star over there.
It's that beat, it's that beat, it's that beat. It's that beat. So
bro, I know this weekend though, when we hit Vegas and we turn up a little bit, you know what? You go with a why? You gonna be taking it with you or not? I mean, hey, but look at, but you want to go out with your friend, but he can't go out with us? Okay. What you think? You think you should go alone? Wait. Oh, see this?
Bring your brother Vegas. Yeah, that's Vegas not off limits.
But what? I'm not bringing no girl. I'm not, but you know, I'm all about business. We out there for business too. We gonna turn up a little bit, have fun, but we still out there with meeting our
moving bars like dogs.
You know I'm gonna take care of them.
Bad like Gladstone.
See, y'all, you was cool going out a minute ago, but then
hits from chick skip.
Oh, do you want to brush your tip?
Hats to Tom Troopers like Krupa. It's that beat, it's that beat, it's that beat. It's that beat. It's that beat, it's that beat,
I know
it's
you
that
is.
beat.
Every time you around, we always making something.
It's that beat. So it's that beat, it's that beat, it's that beat.
Ooh, what you get?
It's that beat. So sweet.
Get the steak or the chicken? Steak, double steak is the best. Okay. I don't know. Chicken is cool, but every time someone has a bad experience with Chipotle, it's always because I got the chicken. They be undercooked. You know what I'm saying? And it ain't seasonal I want it. You know what I mean?
Too many people to mention. God made Clark happen. And amen for
the
that.
valley, okay.
Around the world like moon. Bombing like Bono. Punch it when mom gon' taped up. Slapping skins till it hurts. Double kick start hearts like Jones started hurt. It's that beat, it's that beat, it's that beat, it's that beat, it's that beat.
For real? You a model or what? Why you lying? Look at that smile. You look like a model.
It's that
For real?
beat.
Okay. What you do
So
with it?
sweet. It's that beat. It's that beat. It's that beat. It's that beat.
A year, okay. You ever
It's
thought
that
about doing
beat.
modeling or anything?
It's that beat.
Ever had any like background with it? That maybe like acting probably. For real? Okay. Well, I have a production company and stuff, and a reality network, so that's why I'm working with them too. Yeah, so I want to use this house. I feel like this is kind of the perfect way to do it. I want to do kind of like a real world, like acting, more like in tune with the shit. So that's why we out here. The end of the dog, this is like model for me a little bit. Why are you being shy for? Yeah, I got you. Oh, I'm right here? They want to get some pictures with the car, my car. Good? First, I got you. I bet, yeah. But I've never been inside one of those. Never. Okay,
Tell security, stop! Ask me about security, bro! What is security doing?
See, you need to get like the...
Oh my god! Tell security, no! Tell security, no!
I don't know what you want from me. I don't know what's come over me.
hit you about and stuff like that? Okay. I mean, but you're out in LA. It's easy to run into. I mean, like right now. You out here right now, literally. Oh, okay. Oh, so you do go out here. But then also in the time too. Yeah. Okay. But does he get his own time too? Yeah. Okay. So when you go out, where you usually go? Just with them only? Or just like outside of that, where you go? You said you did the beach spot. Actually, is that the one that has like inside the bar, but then it also has that part on outside too? What's under it? Is there like a I think I have been there though. Is there like a little patio outside or not? Like on the rooftop part? Yeah. And they just get the elevator up there. I've been Yo, I have actually been there. Really? Dude, that's like it's cool now. Okay. I hope so. Ain't no way. That's true. Cover it up to that you'd be with him forever.
QMH, wind, cavalcade, nothing. Visibility, rapid.
I feel like you never look in the mirror. Good, but great is great. That's
I think it's in a random flower. Yo, production folks on one cam. I must go into them. Oh my God, Chad. Everybody scream GG. What if you let it? Nigga kidding me. You just leave, bro.
So for sure, it doesn't matter who you eat. You're gonna fold no matter what. Chris Brown, God, you ain't gonna fold. You never folded with Chris Brown? No. Damn, I know a lot of people that fold Chris Brown. Should dilate on picking up? Was it cool?
How you doing? Nice to meet you. What's up, man? Tell me that
yeah, you hella shy. I was like, damn, this girl kind of.
I just wanted to let you know. I love it. I put you on the road, you said. And you fast.
I'm be real. He was smart how much he loves you by himself. He said the LB is it.
Alright, so this nigga right here.
That's good explanation.
Look. He put you on the road you packed up 2 lives like a flying color. You just trying to see how it is. But you did pretty good. You did really, really good. How does that make you feel though? I mean, you be mad that I be out by myself and you be always texting me and talking about I'm doing something.
You gotta test them next. You gotta test them next then. Let's go.
That's me, I'm big body.
Oh yeah, we all like that. Thursday is not real. Like coming over for the whole party, nothing was real. It was all just for that. It was all just to help people find out. Cameras everywhere, all over the place.
And I told you to get ready. And I said I had a big meeting. And I told me and Oprah had to make sure we had to sign this contract today. I need to be up today. I had you up at 7 o'clock this morning.
That's the
He mentioned to us that you like about a hat in the past.
The whole world knows now. Damn! That means she really loves you. That's crazy.
Rick Owens on the balcony?
Damn!
I love you. Yeah, and he's gonna, that's the whole thing. He's gonna give me the world right after this, right? Where are we going? We're going to David Buster's. That's where we're going. He did say. He was a good talk. Now, he did say he was going to buy you a bag. Yeah. Mark Jacob.
Hey, you put that price tag up there, my boy. Hey.
I just got to release it. I'm so sorry. Well, nice to meet you. Yeah.
an ego, and that comes across.
But look, if I don't go, then
Everyone who's watching, please go and show the love. Go and subscribe.
I feel like he's like a little bit more like.
Again, like I said in the beginning, a lot of people complain that the content.
I was ready to get in there.
I haven't got any excuses. Really want to get in.
But Jack, he's the type. Look, Jack, he's the type. He's gonna go that extra mile, bro. Like, he gonna go that extra mile, like dead ass. Bro, he's gonna go that extra mile, like. He's gonna try to get a kiss and shit. What is the next one?
Next one's in an hour and a half.
Sorry.
Right?
I'm gonna let y'all know. I gotta go quick. Y'all be safe, Mike. Make sure. Alright, bro. Oh my gosh.
Move it.
100. Hold on. Let me Chad, let me get my
Slight difference to know about. There we go. Now you're just touching the side. I don't like that. Look at the views surrounding everything. At a crowd, it's a lot easier when you tell them. Afterwards, the padding of fine. You just use P5 all around the platform, right? Boom. Pass it out. Now it looks a little bit better. Okay, so let's go to the document. Find out how it works. Nice caravan, nice. So,
I said I feel invincible. They like Poppy, what you get to? I'm on a book on wait.
Tuesday, first link in the description.
Chad, let me not even get yeah, we wildin'. We wildin' now. We getting too ahead of ourselves.
I said I feel it's 100 niggas in the spot. It's 85 just to whoop.
Y'all hear her?
Cause a lot of these niggas be I'm for real holy. And I shoot like Robert Hood. I'm off this percolated shit. I got a percolated dick. Percolated dick. I show her this percolated tricks. They know who in the city. Paso, nigga, you can ask them. Paso, super city, titty. Paso, going 50 for 50. I pop a perk over toilet, they shit at the party, then change the artillery. Energy. I'm giving nothing but energy. I give a perky and Hennessy. I get 2 shots to the enemy.
Chad, yes, we gotta restart VOD too, okay? Chad, what today is?
Fucking nigga telling me. I spent 250 on my wrist. I spent 250 on my bitch. Double G, niggas do I'm prepared. Moving inspired, turn everybody crib. DJ, crew. My nigga fuck with the wolves. Tell Spank in and play it back. While the wolves throw the bag. You know I'm shooting for the stars. Aiming for the moon. I shoot at any op. Cause niggas know I'm boom. Send that nigga to the medic. Everything raw, no edit.
Red squares, W479. W479, chat. Red squares.
It's 85.
Everybody saying red squares.
Cause a lot of these
Red
niggas
squares.
I'm for real horny. And I shoot like Robert Horry. I'm off this percolated shit. I got a percolated bitch. I give her this I show her this percolated tricks. They know who in the city. Paso, nigga, you can ask Diddy. Paso, Super City, UTD. Paso, going 50 for 50.
So we've got IDs there. The first title is going to be Get a Ride. The second title is going to be Order Food, right? So this is going to eventually bring about like 21.
Yeah, I said I feel invisible. They like Poppy, what you get to? I pop a brick over retarded.
So right now, wait. Home screen. But once we implement Reality in navigation, it should go to like right? So it's just a sort of demo feature. Right? So you see that's why
I said I feel invisible. It's 100 niggas in the spot.
Today's day 21, bro. I started on November 1st. So whatever the date is good. Alright, that's good. Day 21. Miles, let me know when it's at red. Red. Miles, let me know when it's red. Production, call me for a reset. Production, call me for a reset. ASAP.
I give it a percolated dick. I show her this percolated tricks. They know who in the city. Paso, nigga, you can ask Diddy. Paso, Super City, UTD. Paso, going 50 for 50. I pop a perk or retorted. They shoot up the party. Then change the artillery. Energy.
Yo!
I'm giving her my energy. I give a perky and Hennessy. I get 2 shots to the enemy. Hope you remember me. What the fuck a nigga telling me? I spent 250 on my wrist. I spent 250 on my bitch.
Everybody spam stay. Everybody spam stay chat. Everybody spam stay. Everybody spam stay. Everybody spam stay. Everybody spam stay. Alright, you right? Alright, reset 5.
Aiming for I shoot at any cause niggas know send that nigga to the medic.
So basically this means that we can access
3, 4, no edit.
2,
Paso, did it. I said I feel invisible. It's 100 niggas in the spot. I'm a boom. It's 85 just to walk on. I don't talk to these niggas, cause a lot of these niggas be corny. I'm feeling horny. And I shoot like Robert Horry. I'm off this percolated shit. I got a percolated bitch. I give her this percolated dick. I show her this percolated tricks. Paso, they know who in the city. Paso, nigga, you can ask Diddy. Paso, Super City, UTD. Paso, going 50 for 50.
Touchable opacity is actually a parent component, and inside that I'm just going to say for a quick example text, I'm just going to say item.title, right? So item.title.
Yeah, I said I feel invisible. They like Poppy, what you get to? I pop a brick over retarded. Wait.
Okay? Now, you see how the opacity is hard to see that, but I can't do anything at this point. You can see now.
I said I feel invisible. It's 100 niggas in the spot. I'm a boom. It's 85 just to walk on. I don't talk to these niggas, cause a lot of these niggas be corny. I'm feeling horny. And I shoot like Robert Horry. I'm off this percolated shit. I got a percolated bitch. I give her this percolated dick. I show her this percolated tricks. Paso, they know who in the city. Paso, nigga, you can ask Diddy.